Good morning, everybody, and welcome to the workshop on effects of radiation exposure on offspring and next generations. And it's my pleasure to, first of all, to welcome you all, either here in Budapest or remotely there, all around the world. And this workshop would not have been possible without the support and also sponsorship from ICRP, Melody, and Alliance. Melody and Alliance are European platforms for radiation protection research. I'm pleased to welcome representatives of these three organizing bodies here and to say a word of welcome and tell a bit about their interest in the topic. Please, Werner Röhm, would you be so kind to start?
So thank you very much. Hello, good morning, everyone. Well, this is, as Cisco already said, a joint effort, a joint event, jointly organized by ICRP, Melody, and Alliance. And as I mentioned yesterday in my presentation to the plenary, it's very important for ICRP to collaborate and cooperate with international organizations. And in Europe, the research platforms are really the key players to define the research area and the research done in Europe and financially supported by the Commission. So this topic, effects of radiation exposure on offspring and next generations, is a very important topic for ICRP, but for many others as well, obviously. And that's why the main commission had decided, I don't remember when, maybe last year already, to establish this task group. This is task group 121. It's the most recent one, and it's actually it's the kickoff meeting of this task group. And we are really happy that we could do that together with Melody, because Melody is the organization in Europe looking at low-dose effects. And obviously, this falls within the scope of Melody as well. And Alliance is also there, because there's a lot of interest and input also from non-human biota, from animals, for example. So this is a fantastic example to me how synergisms can provide a bigger result than if we all work alone, separately. So Cisco, thank you very much for organizing and chairing this task group. And we really hope that we will get a lot of important input for the review of the system, because this is the history, or this is the story behind that ICRP, as I tried to explain yesterday, that we embarked now on this review of the system of radiological protection. This will take a while, and this is one of the important task groups, and we need your input. So thank you very much, and now back to you, Cisco. Thank you.
Thank you very much, Werner. And now may I call the chair of Melody, Andrei Wojcik, please.
Yes, thank you very much. Yeah, also from my side as the chair of Melody, welcome to this meeting. We are really happy that it takes place, as Werner said, in collaboration with the other platform, with Alliance, but also, of course, with ICRP. So Melody has, I think it's now 5 or 6 years ago that we started to organize workshops annually. The first workshops were organized just by Melody. And then, of course, we started to grow together and new platforms started to emerge. And now we try to make these we try to organize these workshops as a joint event. And that has, of course, a huge value, because we really work together, and we should work together, and we benefit from the collaboration. So I'm really happy. Of course, the fact that this takes place in Mozart Rome has, of course, something to do with Melody. Just think about this Mozart and Melody. Just to put, I wonder how Alliance will react. Will cope with this. So anyway, welcome again. Thank you very much, Cisco, for organizing this, and I wish us all a lot of success. Thank you.
Thank you, Andrei. So I can remember these Melody connotations. You know, I used to coordinate a European project called NOTE, and the next one was DOREMI. Then the Melody platform was established, and there have been then concert and all these different projects in Europe. So singing together. Okay, so on behalf of Alliance, please, Christel.
Thank you. So normally Nell Horomans from the Alliance should be here to present the Alliance, but I don't know if she's online, but
I'm online.
anything. So I will say a few words about the Alliance. So the Alliance is really happy to be part of this workshop organization. We have a lot of interest in studying the effects of low doses of ionizing radiation. And there is a task group in the Alliance which is called Transgenerational Effects and Species Sensitivity, with several members of the Alliance working on that topic. So, of course, we are really interested in this workshop. And as said by Andrzej, we also organize in the past workshops, and among them, a few years ago, there was a workshop on epigenetics and the role of epigenetics in transgenerational transfers. So we will talk about that today. So welcome everybody, and have a good workshop.
Thank you, Christel. So, as has been already pointed out, this is a very large scope, wide scope for different aspects of offspring and next and future generations. And so we have organized the work also according to have some breakout sessions addressing different topics. And you will hear a bit more about that now by the chairs of the breakout sessions. Perhaps we start with Dominic and the overall presentation, radiation protection point of view of this topic.
If you want. So you should have a presentation in my name. No. Before that, did we check how many people are online? And is it okay? They can 13 online, so 13 people online.
It is okay, we can hear you.
The view of the camera, that's it? Okay. And the presentation as well. Okay. So none of you were in the camera. Sorry, but for the three of us. So maybe we can do it again. No, but we are just outside of the image, which is okay. The sound was there.
That was the right one, yeah. All right, that's right. Sorry. That's it. There's the remote also.
Okay, so this one is only for Group D, but maybe I can. So Group D, as has been said by Cisco just before, we are going to discuss the issue related to heritable effects and effects associated to in utero exposure for both humans and non-human biota. And we separated it in 4 breakout sessions, and the 4 breakout sessions will be Group A, which is dealing with epigenetics and genetics. The second one will be about in utero exposure. The third one will be about non-human biota, and the last one will be about impact on the radiation protection system. And in fact, the proposal by Cisco is to begin with this one because that's what drives. That's the reason why we are there. The idea is that in the next 10 years from now, we are going to have a review of the general recommendation. So the ICRP, and the idea is to prepare some bricks, some parts that are needed to be revised before we end up with this new recommendation. And the review of heritable effects is part of it because it gets into the calculation of the detriment, and it's important to know if the review of the literature since the publication of Publication 103, so the last recommendation in 2007, are changing the things or not. So that's a very rough presentation. That's not the one I was expecting, but maybe you can go to the next one. Yeah, please. Okay. So if we come back to the history, so we can discuss about that. But the first introduction was in 1927. The research by J. Müller. He received the Nobel Prize in 46, and the hypothesis that heritable effects can be induced by radiation was introduced in publication 1 of the ICRP in 1959. What we know, the way it is considered in the system at the time being, so the inclusion of heritable effects in the calculation of the detriment, of radiation detriment, the system as we know it today was in publication 60, so in 1991. And the current system is based on publication 103, so in 2007. And so we can see that there have been a lot of evolution in the knowledge and in the way it has been considered in the radiation protection system. If we look at the recommendations in 2007, the effects of in utero exposure to radiation are considered, but mostly as deterministic effects. So for the fact that the exposure in utero can create some deterministic effects above those thresholds. Heritable effects of exposure to radiation are included as part of the detriment, radiation detriment, and heritable effects on non-human biota are not considered in the system, in the current system. And so there is a need to revise the assessment of the effects of ionizing radiation in offspring and next generation. So, as I said, so we are going to have 4 breakout sessions. So the one we are going to discuss about the potential impact on the system of radiological protection is this one. And the chair will be myself, co-chair Thierry Schneider, and the 2 reporters will be Aidana and Frido Zolzer. I hope Frido is online, so well, nice to hope you can follow the discussion. And we are going to have 4, but this one is more on the breakout session 3. So we are going to have 3 presentations. So the first one will be all heritable effects were quantified in the ICRP publication 103. So in detail, what is the mechanism for the introduction of heritable effects in the detriment at the time being? It will be done by Aidana maybe today in the afternoon or maybe tomorrow morning, I don't know. The second one will be about Thierry Schneider, so addressing the heritable effects in the implementation of the system of radiological protection for both the medical field but outside of the medical field in post-accidental situations especially. And Frido will come with a public presentation about the ethical aspects of radiological protection for offspring and the next generations. So if you're welcome if you want to follow this different presentation, they should be available in the Dropbox at the time being. And the questions for the system is about the impact of on the assessment, which is the first step. That's what I'm interested in. What is the impact on the calculation of radiation detriment? We have to look at how it is calculated in the system right now. Is it still okay today? Are there new scientific results that should change it? Especially the calculation as it is right now considers only genetic effects and not epigenetics. The second one is the impact on the characterization of tissue reactions associated with in utero exposure, what is new, and also for in utero exposure, also, of course, the risk of cancer. What is the impact on the operational radiation protection? So there is an exponential rise in medical exposure, preconception and post-conception, and there is some issues related to radiological protection, concerns about potential effects for public workers and patients, operational issues in medical radiological protection, and the ethical aspects. And of course, consideration of the effects of non-human biota in the system of radiological protection, which is not in at the time being. So that's a very short presentation. I think that's the last one. We can come back to in more details on the calculation of the detriment or any points you would like to raise. So the first step is really to to review the current knowledge about heritable effects and the effects of in utero exposure, and to see if there are some elements that needs for revision of how it is included in the radiation protection system at the time being. Thank you. Any questions?
Are there any questions at this point, or should we just go through the group works, in introductions to the group works, and perhaps then discuss a bit more, and perhaps also to have a look on the questions, whether they are the questions that you like to discuss. Is there something missing, and so on. So I will present now the group A. And yeah, well, Saloma, it's the one that I gave you. That's the one, thank you. So in fact, this is something I prepared for the IO joint IRPA session, but I will not go to the conclusions, but just go through the introductions. So indeed, the group A is going to discuss I should be there. Okay, sorry. Oh, just empty chair. Okay, perfect. So in this group, we are going to discuss the genetic and epigenetic effects. Really looking back to the epidemiological evidence, there isn't too much data. There wasn't 20 years ago when this review was done previous time. There is some new data there, and we will hear today in the plenary session about the TRIO studies and other approaches that have provided more information, especially in the molecular biology, molecular genetics. New methods during the last 20 years have improved the scientific basis, and we should review that. So previously, indeed, the assessment of hereditary risk was based on mainly on animal experiments. And then general knowledge on the human genome and its function. And also in this area, there has been a lot of new information. And studying genetic effects in human populations is extremely difficult. So in principle, a germline mutation may take place in any of the 20,000 genes of a human, and the type and severity of the potential harm due to a mutation vary a lot. And there are also other reasons, not just radiation, that could impact the mutation rate and the rate of congenital diseases. So it's a big challenge, and it might require, in the old days, you would have needed quite a big population to address these, but this has also changed, I think, along the TRIO studies and a new approach. We should also discuss a bit all these definitions, what is meant in the area of genetic epigenetic effects. Of course, we are now discussing preconceptional exposure of germ cells before fertilization. There's another group that discusses from that point on. And heredity, which is called also inheritance or biological inheritance, is the passing of traits from parents to the offspring. And the hereditary effects, nowadays we can identify genetic effects and epigenetic effects. And usually when you use the genetic effects, you talk more about the inheritable changes in the genotype or the like mutation or other markers, biological markers, hereditaries, in fact, passing of traits. And epigenetic effects, they are inheritable as well, but it's really the phenotype, which is phenotypic changes that do not involve alterations in the DNA sequence. And transgenerational inheritance is then the transmission of epigenetic markers from one organism to the next that affect the traits of offspring without alteration of the primary structure of DNA. There's a lot of evidence of epigenetic effects in somatic cells, but not that much in the germline. And perhaps we will hear also from the group that discusses the effects on biota. They have perhaps more evidence there in animals and plants than we have in humans, from humans, and these are of course very sensitive type of studies in humans, human population. When you discuss the cell-to-cell transmission of biological markers from one cell generation to the next cell population, usually it's easy to use either the genetic or epigenetic terminology, but when you discuss the organism-to-organism transfer, then you use the hereditary or heritable and transgenerational, and it's passing of traits. Well, this is just a description of the classical paradigm of radiation injury from the whole, from the whole paper, which is radiobiology for radiologists. So I think that we need to see the DNA damage has been well established as cause for mutation, and then either heritable effects in germline or the somatic mutations leading to cancer. Then we have to discuss what's the role of epigenetics in this timeline. And I think this is quite a big job still to be done. What are the markers? What are the early changes? What does lead to the epigenetic changes induced by ionizing radiation? Is there some sort of repair? And what happens then? And how are epigenetic effects leading to these different types of biological effects and health effects in the long run? So a lot of work to be done there. And well, I don't go to the other areas, but of course there is some dichotomy also in the terminology, where some of the adverse outcomes in the offspring, in child, can be determined either deterministic or stochastic, depending on the context. So this is briefly the group discussion items that we plan to discuss in Group A. First of all, about the epidemiological evidence, then discussing the experimental study design, mechanistic approaches. And now that this is indeed a joint workshop with ICRP and Melody Alliance, We are also interested on the research needs. So Melody typically organizes the workshops to discuss science and future roadmaps for research. And there has been some new knowledge on radiation effects during the last 2 decades. I'm not going further from this slide because we are going to hear the presentations during the plenary session. And for this joint IRPA session, I will be updating this presentation to reflect the conclusions from this workshop. So I think I will now pass the floor to Richard to tell about the work in Group B.
That's it. Great, thank you. Okay, well, I'm Richard Wakeford here, and I'm going to be looking after the in utero effects. So that's Group B with Kimberly Applegate there, who said she's going to stand up, but she just waved instead. Who's going to be looking after the medical aspects of in utero, which of course are very important. Just to open out, just to set the scene really for the opening slides for Thursday, which is, as Cisco has said, we will probably evolve as we hear things in the workshop we're coming to, but it is important, I think, to emphasize that we're actually looking at exposure from the point of conception to the time of birth. So in humans, around about 40 weeks. But of course, if you move between species, if we look at mice, where a lot of experimental evidence comes from, of course, we're not obviously looking at 40 weeks, and we're looking at a different state of development of the organism. At birth in a species like the mouse, so that has to be taken into account. But we're looking at effects in utero which go from a ball of cells right through essentially to the baby. So the development of all the organs and tissues, and that's really quite a big thing when you come to think of it, because what is the effect of radiation exposure on this small ball of cells, the same as essentially the whole organism at birth? Well, it's very unlikely. I think in publication 103 there was some discussion of this. If you have a non-lethal alteration in one of the cells very early on, just after conception, how is that likely to affect the organism in later life? So we go from there to essentially the irradiation of the baby just before birth, and the effects that can produce. So that's a really quite a broad range of effects that we're looking at. So for antenatal exposure, so for in utero exposure, we're looking at the usual, if I can put it that way, of stochastic effects, cancer in the exposed individual, cancer in the late, for exposure in the late fetus, where we do have some epidemiological evidence, and of course hereditary effects also have to be considered for in utero effects. But as I think I have emphasized, the magnitudes of these risks are liable to be different, vary with gestational age, and could be very different indeed. From the irradiation of a ball of cells to irradiation of essentially a baby. And all that has to be taken into account when we're dealing with the risk of cancer and the risk of hereditary effects. But also we have to deal with the developmental effects as we move from this ball of cells just after conception to birth. Genetic effects, developmental effects, and we have to obviously take those into account. Some epidemiological evidence, severe mental retardation in the atomic bomb survivors irradiated in utero, for example. But these are effects that are specific to in utero exposure and are obviously important, congenital malformations, for example. And again, the risk of pterogenetic effects, developmental effects, certainly do vary with gestational age. Severe mental retardation, for example, occurs during the development of the central nervous system. And outside that period in utero, you do not see these effects. So again, it's very important to deal with that properly. So I'm not going to go further. My other slides go into details about these various things of cancer, what information we have on cancer, what information we have on developmental effects, and I will, during the presentation to Irpa, go into these in more detail, and of course we shall be discussing that in the next couple of days. But I hope that in those slides and what I've just said now, give you some indication of the scope of this, which is very broad indeed. And this is quite a set of problems that we have to tackle when we're looking at in utero exposure. So I hope I've set the scene there. And did you want to add anything, Kimberly? Okay, that's fine. So that's me done, I think, Cisco. Thank you.
Thank you, Richard. Oops. We survived. Okay. So may I now ask Christelle to give an overview of the Biota group.
Thank you, Cisco. Yes, that's me. Thank you. So I'm going to present the work that will be done in Group C on heritable effects in non-human species. So I'm sharing this group with Nell Horowitz, who is online. I know that she's online. I don't know, Nell, if you want to say a few words?
Yeah, I'm online. I don't know whether you can hear me.
Yes, we can hear you. So
Okay, that's good. So thank you for being there, Christelle. We will, in the next few days, I have a terrible echo. We will, in the next few days, go over a number of questions that are typical for non-human biota, but I think there are many links to the other three groups, and I'm sure Christelle will give an overview now of the questions.
yes. So next slide, please. Where is it? Okay, so some background information on this topic. So there is a lack of knowledge about the fundamental mechanisms that underlie these heritable effects. And this issue is of particular importance for the biota because in the biota we deal with very different life durations. For example, for a simple worm like Cenorhabditis elegans, the life duration is 20 days, whereas for trees it may be 1,000 years. So the mechanisms of inheritance may be highly different between these different organisms. So there have been scientific reviews for radiation effects on biota, so done by UNSCARE, but also several ICRP reports that have set the basis of the radiological protection system for the environment. Recently, effects data have been reviewed to propose new derived consideration reference levels for environmental radiological protection under the auspices of TG99. But the data on heritable effects have been considered, but have been described as part of uncertainties for the system. So this is something that we have to consider now. And among the biota, when we consider effects on the biota, we do not consider effects at the sub-individual level, but generally we consider effects at the individual or population levels, because the sustainability of the populations is really the more important parameter to protect populations and communities and ecosystems. So what is the parameter that is important to consider the population sustainability? We could think that survival would be important, because if you have one death, you have a decrease in the population, in the number of individuals in population. But modelings have shown that the most important parameter is reproduction. It has really very large effects in the natural environment, and this parameter is the most important parameter to take into account. So that's why it's important to understand the mechanisms of this radio-induced reproduction alterations on one generation, but of course over several generations. So I'm just giving you a flavor of the presentation on Thursday. I have a definition of multi-generational experiment. So I don't know if we have the same definition. In fact, it's interesting to see how we consider these topics and perhaps to find common definitions. So for the environment, multi-generational experiments consider continuous exposure of populations to the stressor for successive generations. So the simplest expectation is that the observed toxicity in the offspring is not greater than that in parents exposed over their full lifespans, at least over the initial generations, and then with a possible development of tolerance over longer time scales. And in fact, there are some examples that have shown that over the continuous exposure of microcrustaceans to gamma external irradiation, over 3 generations, radiation effects on survival, growth, and reproduction increase in severity from generation F0 to generation F2. So there was an increase in severity of the effects. So multi-generational effects were highlighted. Then the other point, transgenerational experiments. So for us, transgenerational experiments consider effects on the exposed generation and on subsequent unexposed generations that have been reared after hatching in stressor-free conditions. So, so you can see here the example for a mice. I don't know if there is more. The mice is bearing the embryo, which is also having germ cells. So these 3 types of cells, let's say, have been exposed at the F0 generation. So until generation F3, you cannot consider that the cells have not been exposed. So cells of the germ cells have been exposed, so the effects may appear until F2, and the embryo have been exposed, so the F1 has also an effect of gamma irradiation. So you can say that a transgenerational effects occurs until from generation F3. It's different for fish or any other type of organisms that has an external fertilization, because as a fish spawn, only the germ cells are exposed, and the F1 generation has been irradiated, whereas as soon as F2 generation, there is no direct exposure of the cells. So these things may be important to consider. And some examples, but I will not go into details because it will be presented on Thursday. The Drosophila is back. So there have been recent publication studying Drosophila that have been sampled in Chernobyl sites in 2007 at varying contamination levels. And these flies have been reared in the laboratory in order to study the transgenerational effects. So the authors have seen that the survival rate of offsprings was still decreased after 160 generations. So highlighting a transgenerational impact of the field exposure that was performed several years before. So I think I will stop here for the scientific part. So say just a few words so about the chairing. So Neil Hormas is co-chairing with me. We have two rapporteurs. Sandrine Frelon, who is online, and also Cheyenne Sritaran, who is a mentee of the ICRP TG 121 group. And we will also deal with several questions about the role of epigenetics in evolution theories. It will be presented by Cisco. We will have a presentation of Sandrine Frelon on the importance of inheritance in the biota for the risk assessment. And also a presentation of Paulus Lannan on DNA methylation in plants. So we'll see in the coming days. Thank you.
Thank you, Christelle, and thank you, Nele. So we heard actually very well the remote participants. So please, if you have any questions or comments from outside the Budapest workshop, please don't hesitate to say a word. So yeah, I forgot to say that my co-chair in the Group A is Manur Prakash Hande, who is present here in Budapest. And I have two rapporteurs, Fieke Dekkers, Fieke there, and Katalin Lumnitsky. So are there any questions at this stage? There was already some discussion on the interchange between the groups, because there are obviously same things we have to discuss, and there will be some visits from groups to the others, and it's not forbidden to visit other groups if there are interesting topics that you want to hear or discuss and make your point. So yes, please.
Yes, thank you for this introduction. I have just a naive question. In your presentation, Cisco, you mentioned that we have no significant knowledge on human and we rely on animals' knowledge. And then with Christelle explains that we have no knowledge about the mechanism. So what to do? And so I know that this is a challenge for the TG, but this is something that we need to clarify and to say to see how to proceed.
Thank you for the comment. We clearly need some discussion and also perhaps agreeing how to communicate things. So any other questions and comments or So perhaps we should now go to the practical arrangements. Kelsey and Aidana have some. But first, Dominic, please.
One additional comment. You presented some definition of the different main topics and main words, and I agree with Christelle. We have to look at it in the 4 groups to make sure that we understand it the same way. And the first task maybe will be to find something which is in agreement for everybody in the different fields, and just to make sure that we are speaking about the same thing when we are using one specific word, which is not so obvious when you read the articles. So that's maybe the first step, yeah.
Thank you, Dominic. I fully agree, and that's one of the reasons that I wanted to write down some of the definitions, and we are discussing these effects in one hand on cellular experiments, and then germ cells is another situation, and we have to be exactly sure when we are talking either one of those, for example. And then humans and biota are different. When we think about the reproductive strategies, there are huge differences, and this may impact the interpretation of the results and how we consider the evidence from animals or plants for humans. So these are certainly things that we need to clarify during this workshop and continue in the TG task group. So we need your input. Any other comments, please? Ludmila?
This comment I also did in our meeting. It's about separation of other factors or other effects. For example, psychological effect, for example, from stress, both for human, for animals. It created the rising oxidative, it's the same similar effects to radiation. So sometimes it's quite difficult if a person suffering stress after accident or if mice are in experiment, they also passing via stress. So sometimes it's quite difficult will be separate, which is related to doses or to stress, psychological stress. So just to keep in mind, and maybe other factors.
Yes, I think that's a very good comment, and if you think about radiation accidents, there are always these 2 sides of the story. There is both the stress and the concern, and then there are the biological effects. And we need to know what is caused by either of them or if they are working together. Any other comments right now? Yes, please.
I will probably just elaborate on something that was said before by Dominic. The terminology from the first few presentations, I could see already that there's lack of common ground. For example, transgenerational effects. Is it sensible to understand under transgenerational effects only epigenetic changes? Why not genetic changes, right? And when we talk about traits, is it sensible to talk about traits and not the detriment? Because some traits cannot represent detriment. And the whole purpose of this workshop, of this task group, is to contribute to the detriment calculation. So should we keep that in mind as a kind of conceptual frame set, that we consider changes, genetic, epigenetic, that related to detriment, disease? So maybe there is a different reading, different understanding, I think, in the room. So I think maybe one of the useful products of this workshop could be an agreed terminology, agreed conceptual vision, what we are looking for, and then that can be discussed in follow-up activities, etc.
Perfect, thank you. Okay, any further aspects, comments? So we have got very good advice already for the continuation of the workshop. So, but are there any now practical aspects that Kelsey or Aidana would like to take up regarding the?
It's always me. Is it possible to have slide 6? One slide was missing in my presentation because it was in the other one. That's this. So, on a very practical point of view, what we need for radiation protection is to make sure that. Can you go on, please? This is the way the heritable effects are estimated, quantified, to be integrated in the detriment. What we need is to know if this equation is still okay today. It includes four parts. The first one is the baseline frequency in humans of different effects. So Mendelian effects, chromosomal disease, chronic disease, including cancer and cardiovascular disease, and also congenital malformation, the 4 categories. And so the baseline frequency is needed. After that, the effect of radiation is here. That's estimated by the doubling dose. It's based only on the frequency of mutation in mice. The third one is mutation component. Are these diseases depending a lot on the mutation or on other mechanisms? And the fourth one is the potential recoverability correction factor, which is the idea is to transfer from mice to human. And these 4 parameters have been estimated in 1990, a little bit modified for publication 103, as far as I remember. Can you go on with one line in addition? Again, one line. And so the risk assessment is only for genetic damages on only 2 generations, because it was considered in 2001 that it was enough. So the question for us is really that for Group A, do we have new elements today? Does epigenetic, which is not considered in this equation, change the things or not? Do we have new information about the effect of radiation, the doubling dose? Do we have new information about how to transfer from mice to human? Do you have new information about the frequency in the human population? That's the different points we need if we want to update the system. So please, for Group A, if you can have, maybe not to have the answer today, but if it's possible on Thursday, it will be fine. Yes. Thank you very much.
Thank you. There's some challenge, but there's still time, and the task group will continue to work on this anyway. But this will be very helpful to have the viewpoints from all of you. And I fully agree that. For any of the, let's say, mutations, cell death, or epigenetic effects, they are not all per se detrimental. So even mutations can be even beneficial. Some of them are beneficial, some harmful, some have no effect. So it's you cannot just think that if you have a mutation, it's necessarily bad, or even the epigenetic effects is even more difficult probably to say what is beneficial, what is harmful, and what is, if it's just adaptation, more or less. But I look forward to the discussions. We start the next session at 10 o'clock, so are there any further aspects, or should we have a short break? Yeah, getting organized. Working arrangements, Aidana, Kelsey.
Good morning. I would like to welcome all of you, those who participate remotely and on site at our conference. Thank you for joining us. If we're back to the program, the workshop held 3 days, and the rooms will held the rooms of Mozart 1, 2 here, 3 and Strauss, and the plenary sessions and the presentations on the transversal topics will be here in the Mozart 2, and after that we will split into the breakout groups with short presentations. And on the last day, on Thursday session, it also will be here at the Mozart 2, and we will also have joint ARPA session, radiobiology section 1, and at the end will be the conclusion. And yes, so it's very briefly, we have a limited time. Yeah. Do you have questions? Okay. Okay, thanks.
Thank you very much, Aidana.
So let's move to the next session, which is general presentations. So we are still in the big room, so in the plenary session, and so the presentation has been pre-recorded by Ritsu Sakata. The idea is to present a paper published less than 1 year ago on the A-bomb survivors. So Ritsu Sakata is online. So thank you for participating to the meeting online. I let you present yourself, and after that we are going to launch the online presentation. Ritsu, the floor is yours.
Thank you. I am Ritsu Sakata. Can you hear me?
It's okay.
Thank you. I am working for Radiation Effects Research Foundation in Hiroshima. Thank you for workshop organizers to giving this presentation opportunity. Yeah. Let's start to my video.
Should we launch the presentation now?
Yes, please.
Okay.
I am Ritsu Sakata from the Radiation Effects Research Foundation, RARF. I would like to thank workshop organizers for giving me this opportunity to make a presentation here. Today, I would like to talk about a paper that was published in the American Journal of Epidemiology last year, with the same title as this talk. Dr. Yamada is the first author of this paper and made a great contribution to an extensive review of the original data in this study. Unfortunately, she cannot give this talk due to her duties administering health examinations to survivors, which is why I am giving this talk on her behalf. An atomic bomb was dropped on Hiroshima on August 6 and on Nagasaki on August 9 in 1945. The Atomic Bomb Causality Commission, ABCC, which was the predecessor of RARF, was established in 1957. From 1948 to 1954, that is from 3 to 10 years after the bombings, the ABCC conducted a large-scale study of pregnancy outcomes among atomic bomb survivors who gave birth. At that time, experimental findings showed that ionizing radiation caused genetic effects. This study of pregnancy outcomes was motivated by those experimental findings For several years after World War II, when this study was initiated, the Japanese economy faced hardships. There was a special provision that pregnant women could receive extra food, and ABCC registered pregnant women to determine birth defects using this. When birth was occurred, the birth reported to ABCC by the midwife or doctor who attended the birth. And within 2 weeks of reporting of birth, an ABCC doctor visited the home to investigate the outcome of the birth. 3 reports from the analysis of data obtained in the study of pregnancy outcomes have been published before the paper that I will introduce today. These reports did not show apparent evidence that the frequency of abnormal pregnancy termination increases with radiation dose. In the first report by Neil and Shaw, they classified untoward pregnancies identified in the study of pregnancy outcomes into non-overlapping hierarchical groups, such as stillbirths of children without major malformations, neonatal deaths of children without major malformations, and so on. The parents were classified by their exposure based on their distance from the hypocenters and shielding. Associations between the exposure and frequency of the observed indicators were tested. Among the 65,431 newborns used in the analysis, 594 had malformations, but no association with parental radiation exposure was found. They summarized their result as there emerged from this analysis no really clear indications that the radiation history of the parents has affected the characteristics of their children here under consideration. The 0.91% frequency of malformations obtained in this study was almost the same as the frequency of 0.92% obtained from the general population studied by the Tokyo Red Cross Hospital. In the next 2 reports, risks were evaluated for untoward pregnancy outcomes, UPOs, as a group. Radiation estimates by T65 and DS86 were used, respectively. Both reports showed the risks for joint parental radiation dose. The latest report by Otake et al. Found a positive, albeit not statistically significant association with radiation for UPO overall. Both analyses have failed to show a significant effect. With increasing opportunities for radiation exposure in medical, occupational, and environmental settings, the possibility of hereditary effects by radiation has been a constant concern. In fact, after the Fukushima Daiichi nuclear power station accident, pregnant women voiced their anxieties over possible effect on their babies. Increases of stillbirths and neonatal deaths among mothers who received radiotherapy before menarche from the Child Cancer Survivor Study, and excess relative risk of stillbirths among children of male workers at the Sellafield nuclear facilities have been reported. On the data of the study of pregnancy outcomes by ABCC, the radiation doses of parents were updated, and more sophisticated statistical methods could be applied. Under these situations, the necessity of reprisal of the data obtained in the study of pregnancy outcomes were recognized. Firstly, a review of the original data was conducted. Of the 76,614 births, new exclusion criteria was applied for all the terminations reported to ABCC that were identified in the review. After the exclusion of 3,000 births that had not been registered at 20 weeks of the pregnancy, 86 births that occurred during the first 20 weeks of the pregnancy, which was before the usual registration timing, 10 births with unknown pregnancy duration or birth weight, and so on. 71,603 births remained in the analysis. We estimated the risks for 3 separate outcomes: major malformations identified at birth, perinatal death within 7 days, and perinatal death within 14 days. DS-O2 gonadal dose was used. The analysis was conducted for paternal dose, maternal dose, and conjoint dose of paternal and maternal doses. Binomial regression models were used for the risk analysis. Excess relative risk were estimated for separate parental doses and conjoint parental doses. Infant sex, city, birth order, consanguinity, parents' age at birth, and infant's birth year were considered in the baseline model. Parents whose doses were not estimated and parents who were not in either city were considered by the inclusion of indicator variables. This table shows the joint distribution of maternal and paternal gonadal radiation doses. 47% of observed births were to parents who were not in either city at the time of their respective bombings. There were 5,200 births to couples with at least one parent having an unknown dose, that is 7%. There were 800 births to couples in which at least one parent had an estimated dose of more than 1 gray. Mean doses were 0.03 gray for maternal, 0.02 gray for paternal, and 0.05 gray for conjoint dose. Among the 71,603 eligible births, 783 births with major malformations, 2,667 births with perinatal death occurring within 7 days, and 2,904 births with perinatal death occurring within 14 days were identified. The most common major malformations diagnosed were 97 cases of cleft palate and cleft lip, 42 cases of single cleft palate, and 62 cases of cleft lip. And these are the same as with major malformations observed in the general population. This table shows the adjusted rates for major malformations and perinatal death per 100 births according to selected characteristics. background prevalence estimates per 100 births, adjusted to reference categories of factors other than radiation, were 0.95 for major malformations, 3.72 for perinatal death within 7 days, and 3.95 for perinatal death within 14 days. The risk of major malformation increased with the value of parity. The risk of perinatal death was significantly higher for a first pregnancy. Children of consanguineous marriages had a higher risk of adverse outcomes than children born to unrelated parents. It seems that mothers older than age 40 years have a high risk of major malformation. Children of younger fathers and older mothers have a higher risk of perinatal death. The prevalence of major malformations and perinatal death varied over the study period. In 1948, the prevalence was 30% lower for major malformation and 30% higher than in other years for perinatal death. It is believed this difference was due to congenital malformations being overlooked in the early period of the study, and then being diagnosed appropriately later with time and experience. Even if the conditions were similar to the postpartum conditions that led to death at the beginning of the study, survival could have been possible by improving nutritional status, hygiene status, and taking appropriate measures as time passed following the end of the war. It is thought that these led to a decrease in perinatal mortality. Boys were shown to have a higher risk of perinatal death than girls. This table shows the main result of the current analysis. The risks were shown for major malformation, perinatal death that occurred within 7 days, and perinatal death that occurred within 14 days, estimated for separated maternal and paternal doses, and for conjoint dose. Risk for major malformation, ERR per gray estimates were 0.28 for maternal dose, 0.4 for paternal dose, and 0.35 for conjoint dose. The risk of perinatal death within 7 days was 0.22 for maternal dose, 0.11 for paternal dose, and 0.14 for conjoint dose. The risk of perinatal death within 14 days was 0.26 for maternal dose, 0.21 for paternal dose, and 0.21 for conjoint dose. All estimates showed positive values, but had wide confidence intervals. These graphs show the repeated paternal and maternal dose responses for each of the 3 outcomes. The dots shows the estimates for each dose category. The categorical estimate for the paternal group exposed to 0.5 to 0.99 gray was significantly increased for major malformations, but not for perinatal death outcomes. For the maternal group exposed to 0.5 to 0.99 gray, ERR was increased significantly for both of the perinatal deaths, but not for major malformations. None of the categorical estimates for the group exposed to 1 gray or more were significantly increased. As I showed on the slide concerning the association with non-radiation factors for congenital malformations and perinatal death, having many children, consanguineous marriage, and advanced maternal age have a high prevalence of untoward termination. Observed tendencies seems reasonable. From this, it seems that the information related to the parents' characteristics was at least collected validly, and outcomes were identified appropriately to some extent. Current analyses were conducted for the data to which corrections were made based on an extensive review of the original data. In the current analysis based on the population selected so as to minimize the potential for bias, there is a marginally significant association between the congenital malformation and conjoined dose, perinatal death within 2 weeks, and mother's dose, and a significant association between perinatal death within 2 weeks and conjoined dose were shown. However, there may be a problem in interpreting this result as a hereditary effect of radiation exposure on childbirth. Socioeconomic status such as poverty and lack of education and maternal factors such as maternal conditions, infection, and obstetrical factors are well-known risk factors for major malformation and stillbirth. The survivors likely faced more harsh living conditions and poor socioeconomic status. Kato reported that among atomic bomb survivors, the exposed parents had less education than the non-exposed parents. Adjustment for socioeconomic status and maternal factors are necessary to evaluate UPO risk, especially when the factors possible to associate with the target of the interest, that is radiation here. However, we cannot conduct analysis considering these important factors, because information related to socioeconomic status was not collected in the study of pregnancy outcomes. The result of the analysis without adjustment for these factors possibly showed the effects, including those deriving from factors other than radiation, as radiation effects. For several years after the war, the entire population of the cities of Hiroshima and Nagasaki were in harsh and unhealthy living conditions that could have affected birth outcomes. The results of the current study were obtained based on data collected 70 years ago in the unique situation caused by atomic bombings. Generalization of the result to radiation exposure in quite different situations in present day seems inappropriate. We conducted the analysis to determine the association between the parents' radiation exposure and UPOs using the data obtained in the study of pregnancy outcomes conducted from 1948 to 1954. All ERRs for parents' radiation exposures obtained in the present analysis showed positive value. ERRs are with wide confidence intervals and did not have enough statistical significance. And the possibility of confounding by unmeasured socioeconomics seems to be high. And there is skepticism about the accuracy of estimates. The results are valuable due to limited data on untoward pregnancy outcomes risk of radiation. However, extrapolation of the result to the radiation exposure in general situations in the present seems difficult due to the high uncertainty of the result and the data being collected under the specific conditions caused by the atomic bombings. Elucidation of hereditary effects due to parents' radiation exposure is expected by evaluation with additional result of experiments, such as whole genome sequence analysis. Thank you for your attention. If you have any questions, I'd be happy to answer them.
Thank you very much, Ritsu, for this very interesting presentation. So, questions? Do we have questions in the chat?
So thank you very much for this interesting talk. Could you just explain to me why highly exposed parents showed less education than low exposed parents?
Thank you for your question. I think because Can you hear me?
Please go on.
Oh, thank you. I think the subject who exposed get some damage from the atomic bombings. We don't have any information about the socioeconomic status of these survivors, but from the cathode study, we think the subject who exposed get some damage for their life. For example, the parents who they possibly lost the family or family for father or mother, then they cannot, and they maybe lost their house. Then they cannot go to they cannot receive high education. That is one possibility, I think.
Other comments, questions? André?
I should stand here, I think. Yes, thank you very much. I wonder whether there was, maybe you said this, but maybe I missed it. Was there any attempts to correlate the risk or the incidence of malformations with the stage of gametogenesis, both for fathers and for mothers?
Thank you for your question, but I cannot hear. Is it a gametogenesis?
Yes, the stage of gametogenesis. So whether in terms, so did you see any time effects in? I mean, I understand that the problem is the lack of statistical power anyway, but did you see any time effects in terms of the incidence of malformations with time after the atomic bombs were dropped? Was there any trend?
I see. The prevalence of the I think I show the distribution by period of the malformation in slide. Slide 11. Slide
that was
11.
recorded, so I will have a look. Maybe the publication as well. Okay, thank you very much.
Yeah, thank you very much.
Other comments? Participants online, don't hesitate to ask for questions.
May I just add a comment?
Yes, please go on with the question.
Gametogenesis. Well, I'm Nori Nakamura. About the gametogenesis. Well, the point is, it is 3 years after bombing that when people started to collect information of pregnancy. So it's all, for male, it's all spermatogonia. And for female, it's resting oocytes that were exposed to radiation. That's my answer. Thanks.
Thank you very much. So,
one short question. How did you calculate the conjoint doses or the conjoint effect of paternal and maternal exposure? And maybe you can give me a short explanation of this.
I am really embarrassed what the biological basis of using conjoint dose. I am totally upset about that.
Conjoint dose is just calculated, just added the estimated dose for mother and father.
Okay. Other questions, comments? I had one question. For the radiation protection system, we always say that integration of heritable effects in the system is just by prudence, because no observation has been made ever among human population of heritable effects. But it has been observed among animals, and so by prudence we integrate some quantity to take this into account. Can we still say that it's only by prudence? Are these results showing for the first time some results suggesting, at least, and more than suggesting in my view, heritable effects in a human population after radiation exposure? Do we have to change this point of view? Do we have these new results, this new analysis of all data, changing finally this paradigm that nothing has been ever observed in a human population?
Thank you for your question, but it is too difficult. Your question is too difficult to answer for me. Is there any comment from Nakamura Sensei?
Professor Nakamura. Okay. Yeah.
Oh, excuse me.
The possibility.
Okay, do you hear me now?
Yes, please go on.
Okay. Let's say, indicating some positive results, that's always easy. At least we have some positive thing. But when there's no positive thing, we will never be able to say there would be no effect. Just accumulating negative results. And that's a big dilemma for me.
Okay, thank you for your answer.
Yeah.
Are there other questions, comments? Should we move to the coffee break? Yeah, so that's a positive answer. So we are going to go for the coffee break right now, and we will be back at. So one last question.
No, it's not a question. Sorry, it's a statement that Werner made me aware of this. And I just talked to Cisco. That it's worth to remind everybody that the policy of Melody and Alliance also has been that there are review publications that are being written after every workshop. So there is no free lunch. So you will the people who are then distributed among the different groups. The leaders of these groups take the lead in preparing review publications. Just to make you aware of it's going to come, but we think that it's very valuable.
Including people online.
Including people online, yes. So don't go to say yeah, right. Thank you.
So thank you very much, and we will come back to the session at 11 now. So coffee break. Thank you very much for participation.
The slides are ready. So good morning, everyone. I'm very pleased to be today, and I realize it is my first in-person presentation after the COVID time, so I'm a bit nervous and also very pleased to have an opportunity to be in the audience. But I'm also thankful to the participants that joined us today online. I was asked to speak about the TRIO studies on transgenerational effects after parental exposure to ionizing radiation in various settings. And this is the overview of the most recent, or that appear to be the most recent data on this topic. So, preparing this talk, I also was thinking about the exposure scenarios and potential populations that could provide the informative insights about our knowledge and our understanding on transgenerational effects after exposure, parents' exposure to ionizing radiation, especially at low dose range. And I tried to compile a list where I placed the populations that, to my opinion, they already provided or could potentially provide additional information on the transgenerational effects in human. And of course, the studies in atomic bomb survivors that appear to be the gold standard in the radiation protection. I listed them first, but I think Dr. Nakamura, he will speak in his presentation about the he already mentioned this study on 3 families among the atomic bomb survivors. There is another large population of about 30,000 individuals who were exposed in the Teche riverside villages as a result of radioactive waste discharges in early 50s in the southern Urals. And this population already have not only the first but the second generation of offspring that can be looked at. Another population that appeared to be understudied, under-researched to some extent, includes residents from the villages nearby the Semipalatinsk nuclear weapon test site in Kazakhstan. Of course, people who were evacuated from the most contaminated territories or continue to live on the radioactively contaminated territories as a result of the Chernobyl fallout in Ukraine and Belarus represent another suitable population for studies on transgenerational effects. From the occupational settings, I wanted to list the Mayak workers cohort, and I want to show and highlight in my presentation the research opportunities that this population provides in terms of transgenerational effects. There were studies on the Sellafield workers that are similar in terms of production and exposure patterns to Mayak workers cohort. And of course, there is their most recent study on Chernobyl cleanup workers and also on children of Chernobyl cleanup workers and evacuees published by the NCI team. And also there is a database on offspring on Chernobyl cleanup workers existing in Baltic states. And I think, Cisco, you're well aware about this, this infrastructure. And I put, last but not least, the medical exposures. What about the offspring born to childhood cancer survivors? This is a very special population, and in my present talk, I will not speak much about that, but I think we can discuss it more through our breakout sessions. So let me start first with the Teche River population, probably because my career in radiation epidemiology started in the on studies of Teche River population, and just briefly to remind you what was the sources and the pathways of exposure in this population. So the exposure resulted from the massive discharges of liquid radioactive waste into the Teche River. So, and all the villages that were situated on the banks of the Teche River were exposed to various extents in a protracted fashion to external and internal irradiation. External from the contaminated ground and the river surfaces contaminated with cesium-137, and internal exposure through consumption of radioactively contaminated food and river water that contained strontium-90 and cesium-137. So about 30,000 people that comprise the extended Teche River cohort being followed up by the scientists at the Urals Research Center for Radiation Medicine. And of course, because the situation took place many years ago, decades ago, of course, it makes possible to trace and follow up not only the people exposed directly, but also their offspring. So the latest study that I could find in the English peer-reviewed literature was published in 2006, and I didn't see any additional data published, again, in the English peer-reviewed literature since then. So this study included 89 families who lived in the Teche River villages in Chelyabinsk region during the period of significant radioactive discharges. And as control, 49 families from non-contaminated rural areas of Chelyabinsk and Kurgan regions were selected, and also 4 families from the Teche Riverside villages whose children were conceived before the discharges started or took place. In terms of parental age, the exposed and control families were comparable, with the maternal age to be somewhat higher in the unexposed families. In relation to parental occupational practices and smoking habits, also the exposed and controlled families were similar. At that time, of course, the Teche River dosimetry system version of 2000 existed, and the individual doses to parental gonads from external and internal irradiation were assessed. So all parents and their offspring were profiled using 8 hypervariable mini-satellite probes that were chosen because of their high spontaneous mutation rate. Mean cumulative gonadal dose for fathers were about 102 millisievert, and for mothers a little bit lower, 86 millisieverts, but they were comparable and also laying in the low dose range. Analysis of frequencies mutation revealed the 1.7-fold increase in the paternal mutation rate in the exposed families as compared to the controls, whereas maternal mutation rate was not elevated. And most of the mini-satellite loci showed an elevated paternal mutation rate in the exposed group. Let me say a few words about this study. As I said, it was done and published in 2006. Since that time, a lot of revisions and changes have been done also to the dosimetry for the Teche River population. I think it is timely and also important to reanalyze, to update the study, and maybe, if possible, and I think it's possible and feasible, to expand this to get additional insights on the transgenerational effects in the Teche River population. And in this connection, I also would like to bring to your attention the existing opportunities to study transgenerational effects among in the MAIAC workers cohort. Because this is cohort and the people comprising the cohort were hired at the main MAIAC Production Association facilities between 1948 and 1982. That's about 22,000 people, and a quarter of the cohort represented by females. They were exposed both to external and internal irradiation over a long period of time. The existing medical and dosimetry databases allowed to create by the researchers of the SUBI in Ozersk to create a database of workers' family and their offspring. So the database of the MAIAC workers' family and their offspring includes 12,000 family couples with the 16,500 offspring. And what is also important, there are biological specimens available for more than 1,000 family trios. And you can see that a very recent publication and the data, I think, I cannot say for sure, but to my knowledge, not been analyzed yet. So, but you can see that there is available information in those two paternal and maternal gonads already reconstructed, and that includes different components from internal and external exposure, both to fathers and mothers. And you can see that although the doses remain in the low to medium dose range, there are some families where the fathers received extremely high doses. Before the conception, conception where the mothers have much lower doses, both due to internal and external exposure. We cannot go to the next slide somehow. Yeah. Okay. So you can see the size of the potential study groups, and this includes 1,000 children with the available biological specimens that reported by Tamara Zizova and her team. And of course, the MAIAC workers, they are getting old, and also their offspring is not children anymore, but still sufficient number of people in these trios are alive and available for the research on transgenerational effects. So moving to another population that was exposed as the result of radioactive fallouts from nuclear weapon testing in Kazakhstan. Just briefly to say that the overall 456 tests been performed, and it included above and underground explosions. 118 above ground tests and atmospheric tests been performed until 1962, and this is the period when the from 1949 through 1962 that dosimetry is considered as the most substantial and significant exposures in terms of individual doses for reconstruction of individual doses. So that's the map showing the location of the villages around the Semipalatinsk nuclear weapon test site. And of course, for the studies on transgenerational effects, the villages that were in the closest proximity to the test site being selected for the analysis. I will start with the first, and also it was one of the earliest study on transgenerational effects in exposed Kazakhstan population and their offspring, where the 43 generation families were selected from the region that the closest to is located to the northeast from the test site and closest to the side point is the control 28 3-generation unexposed families being selected, matched by ethnicity, year of birth, parental age, occupation, parental occupation, and smoking habits. Again, both parents and offspring were profiled with the 8 hypervariable mini-satellite probes. And it was reported that in parents and in offspring born to the exposed parents, the increased, statistically significant increase mutation rate being observed. In parents, 1.2-fold increase, and in first generation offspring, it was 1.5-fold increase compared to the unexposed families. That gave a ground for the authors to conclude that possible explanation of this increased mutation rate could be the exposure to ionizing radiation, taking into account that the compared families, exposed and unexposed families, were similar in terms of other non-radiation factors. I should mention that there was no individual dose available for in this study. It was just an assumption that people living in this region, in this rayon, they have the highest dose to ionizing radiation due to their location, their proximity to the nuclear test site. Another hypothesis that been raised in this study was about what is the effect of in utero exposure that some of the F1 children could experience. And because, again, they continue to live on the contaminated areas, and the exposure could continue not before the conception, but through the intrauterine period. So this is also another important question that relevant also for the tetrariver population as well. Another study on 3 generations exposed as a result of nuclear tests in Kazakhstan, been published in 2017, and that includes the analysis of cytogenetic abnormalities. 2 most contaminated villages that located about 100 kilometers away from the nuclear test site being selected. This is the village of Dolony, where the external dose for the residents of this village were estimated used on TLD measurements in bricks, cesium-137 measurements in soil, and also tooth animal measurements using electronic spin resonance methods. And the assessment of external doses for the residents, again, it's not individual, it's just for the village, doses for the village. They vary from 140 to 450 milligray. Another village that been selected for the analysis for the study, it's Sarjal, and their external doses was assessed to be about 200 milligray and even higher. So the first generation offspring included 80 people, 35 men and 45 women, all aged from 42 to 53 at the time of cytogenetic examination. These people were born in the period from 1962 to 73, and their parents were exposed, either mother or father or both. Also, data was available on the grandchildren or children of F1 that included 35 people, 15 men and 20 women. At the time of the cytogenetic examination, they aged from 33 to 43 years old, and they were born in the period from 74 to 1984. The control group represented 55 people of F1 and 25 people of F2, born from the non-exposed parents who lived in the village located 700 kilometers east from the nuclear test site. The individual interviews were performed to all the study participants, and the information on occupation, smoking, alcohol consumption, diet, consumption of medication, their past and present history of the diseases, history of diagnostic radiological exams within 6 months before the chromosome examination, all this information been collected. So the analysis, chromosome analysis, included two approaches. The first one was done to assess the unstable type of chromosome aberrations, fragments, chromatid type aberrations such as breaks and exchanges, using routine methods on a total of 58,500 metaphases from 195 study persons, and also stable type chromosomal aberrations being assessed, including chromosomal translocations, deletions, duplications by FISH method. But this was done only for 55 F1 study subjects due to the the very high cost for the method. The results show that there are some statistically significant changes in the frequency of unstable chromatid aberrations detected by FISH method between the F1 and F2 generation from Sarjal and Dologne, the exposed villages, compared to controls. Also, there was observed some significant difference in terms of stable chromosome aberrations, that namely deletions, duplications, and translocations, again in both contaminated villages in comparison to the control group. So again, analysis of role of other non-radiation factors allowed to conclude that the observed increased frequencies of chromosomal aberrations in the exposed villages could be due to the ionizing radiation exposure. What I can see as looking at this study is that there are a number of limitations that probably we should interpret this finding with caution. And first of all, that's the number of families that were in these studies that was relatively small, and especially taking into account that they were exposed mainly in the low to some extent moderate, but predominantly low dose range. The other limitation of these findings is the lack of individual dose reconstruction, and I think it's very important when we talk about the transgenerational effects to have as much as possible precisely reconstructed individual doses. Also, as I mentioned, that was acknowledged by the authors of these studies, that the possible effect of in utero exposure on F1 cannot be ruled out when interpreting these results. What is important to highlight about this population in Kazakhstan, the research, this population remains quite understudied, to my opinion, and it has the potential to provide more information about, including the transgenerational effects. So I put on this slide a table that summarizes the amounts of exposed individuals and their children and their grandchildren. That information, individual information, is available in the database of Research Center for Radiation Medicine in the city of Semey. They performed the systematic follow-up and collect information on on vital status and disease outcomes in all members of their register that includes almost 351,000 individuals. Again, you can see based on the year of birth that this is the aging population, but still it gives an opportunity to to get an information on transgenerational effects among them. And I also want to mention that there is 600 trios established, and these trios, they also have the biological specimens collected. That includes blood samples and also DNA samples. But again, this data had not been analyzed yet. So now moving to the Chernobyl accident and the most recent study that was published on Chernobyl trios. So this is clearly a large-scale, a comprehensive effort to explore germline de novo mutations in children born to parents exposed to ionizing radiation from the Chernobyl accident. And the study included children born to cleanup workers and evacuees from the town of Pripyat and other settlements located in the 70-kilometer zone around the Chernobyl nuclear power plant. The total of 130 children from 105 mother-father pairs with various combinations of parental exposure status been included. So these children had only fathers exposed, only mothers exposed, both parents exposed, and neither parents exposed combination. A very impressive work was done to reconstruct exposure doses for this study, and we have one of the experts who worked on the study dosimetry. So all the questions about the doses should be addressed to Vadim, who is in the audience. And I just want to highlight the important parameters of fathers and mothers' exposure to gonads. So the range, you can see that it was a wide range of gonadal doses for fathers, going up to 4,000 milligray, with a mean dose of 365 milligray. Mothers' doses were at a lower compared to paternal gonadal dose, reaching the maximum of 550 milligray and with a mean of 19 milligray. The aged exposure of fathers ranged from 12 to 41 years old, and mothers' aged exposure ranged from 10 to 33-year-old. Paternal age at conception was of 29 years old for fathers, and for mothers 27 years old. I also should mention that 52% of children were born before 1992. So in the first 5 years after the Chernobyl accident. These included, the group of 130 children included 58 female and 72 male. 23 families had 2 or 3 siblings, but there were no twins in the study group. So it was performed Illumina paired and whole genome sequencing, SNP microarray analysis, and also relative telomere length assessment to characterize, to study the transgenerational effects in the offspring. So all putative de novo mutations that passed the filtering criteria were examined manually, and the total number of de novo mutations was counted for the following classes that representing the distinct mutational mechanisms. That included single nucleotide variants, small insertions or deletions, indels, complex variants, and also single nucleotide variants, indel clusters. So, very extensive analysis has been performed. Although the most consistent result, or the significant finding, was about the parental age at conception, especially paternal age, that expressed a most significant effect on de novo mutations in the offsprings. Nothing were found, neither for maternal cumulative radiation dose nor paternal radiation dose. Also, not much was seen in relation to the father and mother smoking histories in relation of de novo mutation rates. Additional analysis with using the parental gonadal doses didn't reveal any evidence of association between the parental dose and de novo mutations. So truncation of the dose at 1 gray didn't make any significant changes on the overall results. Also, the log transformation of the gonadal dose had no effect on the results. So again, the authors concluded that they didn't see an effect of radiation on the specific classes of de novo mutations in this study, that paternal age remains the strongest contribution to de novo mutations. Also, the de novo mutations increased with maternal age as well. They didn't see any association between the leukocyte telomere lengths in relation to paternal dose, but it was an indication of a possible effect of total maternal preconception dose on the leukocyte telomere lengths. But again, this finding should be replicated and should be reproduced in another studies. So overall conclusion was that individuals in the study do not appear to experience elevated de novo mutations from their parents' exposure. So I was thinking about the data reviewed and tried to summarize the important, to my opinion, points where we are now about the transgenerational effects of ionizing radiation in humans. And it's clearly that it remains an uncertainty and lack of concordance between some studies in relation to presence or absence of transgenerational effects in offspring of exposed parents. There is a strong need for subsequent studies, especially in the populations that I try to highlight in this presentation, that were not sufficiently studied. And they have a potential to provide additional insights in terms of transgenerational effects in humans. Also, it is very clear that as much possible accurate and robust dosimetry, individual dosimetry, is crucial for the studies of transgenerational effects. And just to conclude my presentation, I think that a comprehensive, large-scale efforts, they could meaningfully contribute to international research on transgenerational effects following paternal preconceptional radiation exposure. And this is the last slide, and thank you for your attention.
I think what we'll do is, that's dangerous, hold questions to the end. We have a little discussion period, so thank you so much. And I want to ask if we are able to try Dr. Nakamura's talk again. And
Ladies and gentlemen, it is my great pleasure to have an opportunity today to give a talk. The title may be a bit provocative, but this is not what I wanted, but Dr. Richard Wakeford suggested. My talk consists of 4 parts, namely brief summary, oocyte problem, mutation induction rate, and human dominant mutations, and summary. This slide shows a quick review of past studies. In the mouse, so-called specific locus test was widely conducted since 1950s, and the results are positive for female mature oocytes and male germ cells, but not in immature oocytes. In humans, epidemiological data on birth defects are mostly negative in studies of atomic bomb survivors as well as cancer survivors. Recently, whole genome sequencing studies are conducted, in the mouse, small insertion and deletions, and multiple changes in a short sequence, which is called multi-site mutations, are reported to have increased, but not in humans, which includes 3 families of atomic bomb survivors and about 130 children born to Chernobyl survivors. This slide shows the experimental scheme of mouse-specific locus test. Wild-type animals are exposed to radiation, and then they are mated with mice that are homozygous at 7 specific genes that are related to external phenotypes, such as coat color or ear shape. This slide shows the outcome of the specific locus test. Mature oocytes are the most sensitive at doses above 1 gray, followed by spermatogonia. Reducing the radiation dose rate was found to reduce the mutation frequency to 1/3 in males and 1/20 in females. Impressively, immature oocytes were found not to show increased frequency of mutations. This picture shows a cross-section of a human ovary. Immature oocytes locate near the surface of the ovary, called cortical region, where blood vessels are so few, which is likely to be hypoxic. This slide shows a recent findings that artificial differentiation of multipotent stem cells into mouse oocytes became possible by mixed culture of the stem cells and somatic cells from an ovary. Then obtained oocytes can be fertilized in vitro and transferred into foster mothers to produce healthy offspring. One important drawback of the method was that the obtained oocytes had already started maturation processes and not at a resting stage. A few years later, in 2019, this problem was solved by culturing the cells under low oxygen conditions, from ordinary 20% to 5%. It has been known that stem cells require a low oxygen environment to maintain undifferentiated conditions like hematopoietic stem cells in bone marrow. Thus, it makes sense that immature oocytes reside in a hypoxic microenvironment in both mice and humans. This slide shows cross-sections of human ovary from various ages. The red arrows indicate blood vessels and blue arrows indicate small oocytes. The left panel shows an example of an ovary of a young woman. You see 7 small follicles and only a few blood vessels. The right panel shows an example of an ovary of a woman of 40 years old. You see many blood vessels while no small oocytes are seen. This slide shows that in an ovary of a young woman, the distance between nearest blood vessels and the small oocytes can well be longer than 100 micrometers, which corresponds to hypoxic or anoxic areas in a tumor. Let us move to part 3, which is related to male spermatogonia. Although the specific locus tests were widely conducted, it was recognized that the mutability of each gene varied widely. The black bars here represent original 7 genes, and white bars indicate other genes that were investigated later. Quite clearly, mutability of each gene varied extensively, and curiously many genes did not indicate radiation induction of mutations. Compared with the mutation induction rate and the initial 7 genes, an extended study for a total 34 genes, which include the initial 7 genes, showed that the mean frequency decreased to about 1/2 of that and the initial 7 genes, namely from 2 × 10⁻⁵ to 1 × 10⁻⁵. More recently, we undertook a challenging study by using a 2-dimensional geoelectrophoretic method of DNA fragments, which enabled us to examine 1,000 genomic segments per mouse. The finding was discouraging. I mean, so few mutations could be detected, and the estimated mutation induction rate per gene or DNA segment was on the order of 10 to the -6, lower by 1 order of magnitude than the mean of original 7 or 34 specific genes. Now we move to part 4. Humans do not have marker genes such as good color genes in rodents. Thus, to investigate genetic effects of radiation, looking at dominant changes are the only choice, because ionizing radiation causes DNA breaks, which may lead to deletion-type mutations rather than base change-type mutations. I got interested in knowing the number of genes whose loss of one copy causes a dominant phenotype. These genes are called haploid-sensitive genes or haploinsufficient genes. I look at the website Online Mendelian Inheritance in Man, abbreviated as OMIM, the most comprehensive encyclopedia of human hereditary diseases, and try to list up such diseases. I could find at least 500 such genes to cause hereditary diseases under the conditions of losing one allele of the gene. Of course, such genes whose patients are so few, there will be no way to know exactly if it were caused by a haploinsufficiency or altered gene function resulting from amino acid substitutions. Also, for those genes whose loss of one copy makes the embryo lethal, no patients will be reported. Therefore, I assumed that the true number of such genes can be somewhere between 500 and, say, 2,500, 5 times of 500. This is just an arbitrary. If we assume that the mean mutation induction rate is 10 to the -6 per gray, and the number of the target gene is 500 to 2,500, then one would expect the frequency of dominant mutations in the F1 offspring is 0.05 to 0.25% per gray. It is noted that the spontaneous frequency of human malformation is 1 to 3%, and the genetic contribution is not large, for example, 20%. Therefore, it is understandable that detecting the mutagenic effects of 1 gray exposure to human spermatogonia would be a difficult task. In this regard, it may be worth mentioning that in the mouse spermatogonia, it is estimated that acute 1 gray exposure would cause dominant mutations at 0.34%, which includes bone malformation, cataract, and birth defects. Another source of information that mouse genome does not mutate mutate easily comes from our recent study, which used array CGH. CGH stands for comparative genomic hybridization, and the technique detects altered copy number in small segments throughout the genome and the whole genome. Among 100 offspring born to 4-gray irradiated males, we can detect 5 deletions, while only 1 among 100 offspring in the control group. Therefore, although the number of mutants is so small, the frequency of genomic deletion was something like 1% per gray. Very interestingly, this 1% fits closely to the frequency of reported autosomal recessive lethal mutations by Luring et al. In 1971. This slide shows chromosomal locations of the 500 genes in humans that can lead to dominant diseases if one copy was deleted. It should be noted here that when multiple such genes were included in one large deletion and lost, it is likely that the effects of each deletion would be additive, and hence such mutants are very unlikely to survive. This is the summary slide. First, it seems clear that immature oocytes are resistant to radiation-induced mutations in both mouse and human because they reside in hypoxic areas in the ovary. Second, ordinary genes do not mutate as expected from mouse-specific ROX tests. Third, humans are different from mice in various aspects. For example, we have no hypermutable marker genes like coat color genes in mice. Mouse cannot selectively abort abnormal fetuses, but in humans, malformed fetuses are selectively lost during fetal life. Namely, malformed fetuses consist of about 10% among spontaneous abortuses in early stages of pregnancy, whereas it decreases to nearly 1% at birth. Last, deletion cannot be too large to include 2 or more haplosensitive genes for survival, because each mutation is expected to affect additively. Thank you very much for your kind attention.
If Dr. Murray, you're still with us, we appreciate having questions now. I don't know what time it is. No, in
Oh, here? It's 7 o'clock in the evening.
Oh, okay, it's not so bad. Oh,
Not
it's
so
nice
bad,
to see your face. Thank you for joining us. I don't know if we could take questions for him then. Richard, you might have a question. I just liked your summary slide, and I was thinking about some of the lethal congenital anomalies that we see in humans where we have trisomies that are lethal at birth. So you're exactly right that we see these trisomy 13s, or, I mean, now, unfortunately, we can have them survive, but they don't do very well. You know, modern medicine is, quote, a miracle, but it's not also good for the families to take care of them. But I would still call them lethal. Oh, yes.
I think I should stand there. Thank you very much. That was a very nice presentation. One thing that I think you didn't touch upon, and maybe you could comment, is the problem of strain difference with respect to the occurrence of these transgenerational effects. I mean, we see, I think we see quite distinct differences between inbred mouse strains. So how can we draw? Yeah, can we draw any conclusions about individual risk among humans from these differences?
When you say strain difference, well, what is your endpoint?
Malformations, for example, in Essen, you may remember.
Okay. I know there are specific strains of mice which show very highly sensitive to insult. But I don't know how it can be applied to general population in humans. You may probably know Nomura's data. And, well, certain strains of mice may show something quite different from others. But how is it possible to apply that information to humans? I have no idea.
Neither have I. Thank you.
We just pass it to the next person. Somebody else had their hand up in the back, I think. No? Richard? No? Yeah. Dominique?
Yes, thank you for your presentation. Coming back still to my equation, which is used in the calculation of heritable effects for the radiation protection system. From what you presented, what are the changes in the different parameters? Does it change completely this equation, or are there some elements in this equation that have to be modified?
Well, I don't like mathematics, but I like biology, and I have been puzzled, embarrassed for many years by Dr. James Neal. He's quite good at mathematics and told us many things, but I don't quite understand how is it possible to estimate the radiation risk based on non-significant results. Well, I can vaguely imagine we may estimate upper limit of maybe I'm wrong, lower limit, but some range, even if we're using negative sets of data. But anyhow, in humans, as long as we don't see clear positive evidence, estimating the risk in human is really a hard job.
Okay, thank you. Anyway, that's a point we can discuss in the long term, I'm afraid.
Right. If there are no others, I think we'll go on. This excellent presentation and gives us some ideas. We'll go on to the final presentation by Dr. Herzig. And the title of the talk is Epigenetic Mechanisms and Cancer Risk in Future Generations.
Thank you, sir.
Oh,
okay. Well, first of all, I would like to thank the organizers, Dominique and colleagues, for inviting me. It's a pleasure, but it comes with a cost, and that's I have to explain in 20 minutes, the epigenetic mechanism of transgenerational inheritance. So this brings me to the famous saying 20 years ago, epigenetics is useful if you don't know what is going on. Well, if you know what is going on, then you call it differently. Well, now we actually have some consensus what the epigenetics is about. Defines all heritable changes in gene expression that are not coded in DNA sequence. In contrast to genetic changes, these alterations are in principle reversible, and of course they have implications in understanding mechanisms of carcinogenesis, discovering biomarkers, targets for therapy, prevention, and so on. So these are the three main epigenetic mechanisms. And often we do profile DNA methylation, we say we do epigenomics, and we forget sometimes about histone modifications that are also important, or RNA interference, more recent, and fertile area research. And there is a crosstalk and tight interaction reinforcing crosstalk between the three mechanisms. So, as I said, the impact on the gene activity might be equivalent. For example, if you methylate in a promoter region, you can switch off the gene, so the gene doesn't work. Like mutation can do the same thing, except that this is potentially reversible. We can reactivate silence gene, and therefore there is interest in reversing the epigenetic effect in therapy, but also in perhaps some sort of precise or targeted prevention. So epigenetics, we have a genetics, so it's kind of hardware, stored information, and then we have different software. These are different how the mentions are organized, exploited. So the epigenetic can be seen as a software, and so we can have many different epigenomes that define the tissues and lineages for using essentially the same genome. So what is interesting that for example, even genetically identical twins may be disparate for a disease, and although the same genome, they might have actually different susceptibility. What is interesting, as they share the environment less, the epigenomes seem to be more diverse, suggesting that environment actually has a much more impact on the epigenome and the susceptibility to disease. So this can be illustrated like you have a pair of socks. Usually you wash them together, but if you somehow unpair the socks and you wash them in different environments many times, if you do it many times, you will end up actually the same pair of socks actually with very different colors. So the fabrics is genome, our genome is identical, but the epigenome can be quite different. So we can look at these colors, if you like, using this new technology to guess what environment we were exposed to. So, and that's what we actually trying to exploit in terms of the phenotypes, signatures, and environmental exposures to discover suspected, but also the new risk factors that might be causing the different diseases. So this is our overall themes, trying to focus on different exposures. We also have more recently interest in radiation, but also external endogenous exposures. Of course, the windows of susceptibility are supposed to exist, and so therefore looking at the epigenome can actually tell, because the epigenome may act as a sensors of exposures, but also the mediators of the outcome. We are trying to connect this to the cellular processes, hallmarks of cancer, and to establish causality to different associations that are identifying epidemiological studies. So more recently, the epigenome or epigenetic changes are recognized as one of the key characteristics of carcinogenesis. And that's of course important in evaluation of carcinogens. I wrote, and I was arguing for this in our monograph program at IARC. And when we reviewed basically the evidence about the epigenetic mechanisms involved in different carcinogens, recognized carcinogens, including genotoxic agents. So the agents that actually induce the damage, DNA damage, they may also act in parallel through the epigenome. And for example, here is the ionizing radiation You can see here that at the time, there were quite few papers showing that the exposure to radiation can actually also, ionizing radiation can induce the epigenetic changes. Now this evidence is accumulating. So many studies, of course, more studies are done actually on the tumor tissue, and that's just illustrating the scale of the regulation of the epigenome. This is our recent study on esophageal squamous cell carcinoma. You can see hypo or hypermethylation across the different chromosomes. Of course, it's important to distinguish the drivers, so functionally important from the passengers. And so we are doing this, of course, in the context of different projects. But also there is signatures. The epigenome actually seems to be also deregulated depending on the signatures. For example, this is the in head and neck cancer associated with HPV, or in normal mucosa of the stomach that are actually infected by the Helicobacter pylori. And what you can also see that there is a reversibility. So if you remove the Helicobacter pylori from the stomach, you seem to reverse the epigenetic changes that are induced. So this is an important feature of epigenome, as I said earlier. But the epigenome may have some positive effect. For example, this is our recent study on large study on coffee and tea drinker. You can see association of specific hits that's associated with the coffee drinking. Of course, this might be positive. They might explain some positive impact of coffee on liver metabolism and so on. But it just illustrates that using the new technology, large-scale population-based studies, and the exposure information, high quality, can actually tell us about the signatures of different risk factor exposures. Now, there's something more interesting to us today. We are also studying the impact of in utero exposure on the epigenome cancer risk in later life or potential next generations. The idea is that because the epigenome undergoes profound reprogramming during in utero life, because from one cell or with the identical genome, you can actually have all different tissues. And this is all epigenetic affair, if you like, and therefore it might be very susceptible to different exposure that can actually reprogram or impact the epigenetic reprogramming, and actually can constitute risk to the diseases in childhood but later life. So, so the idea is to actually put together large population-based study or different cohorts to create consortium of cohorts, prospective cohorts with the high quality information about exposure, and then also biospecimens, so that are collected at birth, and then combine this with the epigenomic technologies to associate these omics profiles with intermediate phenotypes or tumor. So I just want to give you one example how the extreme exposure like tobacco smoke that is non-carcinogen, that damage DNA, can also have a dramatic and specific impact on the epigenome. And this is the large study where we put together 13 cohorts of over 6,000 mother-child pairs, and you can see 6,000 DMP, differentially metal deposition. And this is the top hit, aryl hydrocarbon receptor repressor with p-value. You can see the p-value when we talk about, you rarely see this in any studies. With that confidence, you can say that the methylation of this gene in the cord blood of the baby is actually born to the mother that smoked during pregnancy. We see the same because in adults, we used a similar study with adults and including ex-smoker. And you can see here the same gene that actually after quitting smoking, even 30 years after quitting, you can see actually you can establish that this was a former smoker, 30 years. And so this how many divisions you can imagine. Blood cell live only a few hours, a few days, and we are talking about years after quitting. So it must be stem cells, hematopoietic stem cells that actually remember the exposure and propagate this exposure for the rest of the life. But we also see the specific methylation changes that predict the cancer risk at birth. So these are the normal samples taken at birth, and then we look how they associate with the cancer risk later in life. So this is now we are trying to publish this, and this was quite a large study. So now talking about transgenerational epigenetic inheritance. So that's more another layer of complexity, because that's something what I'm not sure the colleague actually wanted to establish the kind of nomenclature. And so transgenerational epigenetic inheritance would mean that it's something that goes beyond F2 generation. So this is the F1, if you like, mother, or P0, sorry, maternal exposure, fetus, and reproductive cells in the fetus. So if you talk about the, we have to distinguish the intergenerational, or at least for this purpose, intergenerational epigenetic inheritance is transmission of the epigenetic marks from parents to offspring to F1 or F2. So depending whether this is, of course, father or mother. And then transgenerational would be actually transmission of this information across generation beyond the limit of intergenerational. So basically that you transmit something that is actually not exposed directly, because if you talk about germ cells of the fetus, this is not transgenerational, so it has to go beyond that. So I think that's something that we really have to keep in mind or agree on this. So this is actually illustrated here. So imagine exposure of the parents, female or male, and then you see up to here, this is all intergenerational. If you see the phenotype is actually transmitted up to here. If you lose phenotype beyond that, basically this is only intergenerational, and transgenerational would be if it goes actually beyond and for future generations. So there are many examples of the phenotypes that is transmitted by the epigenetic mechanisms. For example, this is famous agouti color, coat color of the mice. But this is one of the landmark paper or landmark study done by Skinner and colleague, Michael Skinner, that treated the rats with the vinclozolin. That's one of the antifungal agent used to be used in agriculture. But and this is supposed to be endocrine disruptor. So he established actually that the phenotype can be transmitted beyond a third generation and so on. And he repeated this in different contexts and so on. And he argued that this might be going through the epigenetics. It is, for me, I'm still have a little bit hesitation to accept this, because you cannot rule out alternative mechanism and so on. But there is an evidence. This is many examples of transgenerational epigenetic inheritance with different molecular mechanisms, including plants, for example, famous tomato ripening, mice with obesity, fruit flies, most famous, goes over 50 generations and so on. And the mechanisms are different. So it could be DNA methylation, could be histone, and even non-coding RNA and so on. So I don't want to go into too much details, but there are different mechanisms. There's, for example, naturally occurring in different plants and so on, or induced and so on. So the epigenetic mechanisms are really important for the transmission of the inheritance. One important thing, and it's challenging in this consideration, is the reprogramming that happens. As I mentioned, there are two waves of reprogramming. For those that are not experts in embryogenesis. First one, after fertilization, there is complete demethylation, and there are other layers also affected of the, so it looks like we erase all the marks, and then we set up later on, and there is another one in primordial germ cells. So how the transgenerational effect, if it exists, actually escape this reprogramming or the demethylation? So that's a real challenge. But we know one hint comes from the imprinting genes that actually escape this demethylation. So there are more evidence that there are other regions, or even some histone are not completely, histone nucleosomes actually are not completely removed during the spermatogenesis and so on. So as I said, there is abundant evidence for intergenerational, but the relevance of transgenerational actually epigenetic inheritance has been more limited and even controversial. So I think we have to keep in mind, so there are more studies. And then, as I said, this is in part due to difficulties in proving that the phenotypic difference are really epigenetic and not genetic or whatever, some other mechanisms. So I don't want to really torture you with too much with this mechanism, but since this is the topic, just two examples how this transmission could take place. So there could be, we have to distinguish between so-called direct replicative transmission. So for example, DNA methylation is basically directly copied on the new strand. As you replicate DNA, all the methylation actually is mirrored and copied by DNMT1 enzyme. So this is replicative transmission. And the other one is so-called reconstitutive transmission. So more indirect, but also important. So the really challenge is to establish which of these mechanisms are operating in different transgenerational transmissions. So that's as I was just explained, that's the replicative. So you see that this really works very well established, described. When you replicate DNA, methylation is actually on the new strand is replicated the MT1. So for the reconstructive transmission, this is something that works apparently with different molecules, including histone modification and also non-coding RNA. But this is a little bit more difficult to study than compared to DNA methylation because of technology. So we also have to consider this in the context of broader exposures, and towards we are moving towards exposome research, and actually something that those studies on low dose radiation, including medical, environmental, occupational radiation sources, should be integrated in this, and actually new technology and something that also I think Evgenia mentioned, more integrated approach would be necessary, where we can actually put together different populations or cohorts and so on. So I just want to kind of summarize. The epigenome is now considered as a mainstream in cancer, in research in general, in modern biology, but in particular in cancer research, and it's considered as an interface between the genome and environment. I've shown some examples. It's profoundly altered in cancer, so it goes beyond epiphenomenon. It is important. And also looking at the epigenetic maps, we can establish a signature of different exposures that might be exposure of risk or exposure of or marker of exposure or outcome. So there are many examples of the transgenerational epigenetic inheritance, but the mechanisms are being kind of more worked out more recently in different species. In human, of course, it's much more difficult. So the existence of the transgenerational epigenetic inheritance in humans is still debated because it's difficult to study this in humans and mammals in general, due to extensive reprogramming during embryogenesis, as I mentioned. we need further studies to gain insights, really how this works and how this is linked to the disease risk. Obviously, model organisms, including mouse, rats, and so on, and molecular epidemiology study should prove instrumental in studying how the environmental insults, including the different pollutants, pesticides, low-dose radiation, may impact the health and the disease nowadays. So just want to acknowledge my colleagues, obviously, it's a very important slide, and many collaborators at IARC and external collaborators as well. Thank you very much. So,
Thank you. Thank you. And I think we want to open it up to more discussion, and especially to follow back to Evgenia's talk. Does anyone want to ask questions of Evgenia and also of our speaker just now?
Yes.
It's not a question, it's comment, because actually this comment was arising before, but when you were speaking about this escaping mechanism, so maybe a task aims of this work group, not only looking for detrimental effects, but also this kind of resilience factors. So it will be very good. Adaptive factor is, yeah. Okay.
So yeah, that's important point, because to distinguish something that is a simply adaptation from some kind of there are differences, there are individual differences. This actually implies and that was something that we had a really big discussion about the integrating the epigenetics tools, because now we have assays. You know, before, when people would evaluate carcinogens, they would use the evidence based on the existing genotoxic assays. So they will look, as some of you described, translocations, micronuclei, and so genotoxicity, classical genotoxic assays, which is fine, but it doesn't cover a range of the agents that actually may not be genotoxic, and they may impact the epigenome. And therefore, the challenge was to establish what is the reference epigenome. Okay, genome we know, we sequence, it's very relatively simple to sequence, TCGA and so on, but what is the reference epigenome? And then what is a kind of physiological variability? That was a challenge. Now I think we have even that, because there are different major international projects that actually establish reference epigenomes against which we can compare, certain series of samples with exposures and so on. But indeed, the epigenome is actually adaptation to some extent, but then also it could constitute a risk when the genes are altered in an unscheduled way. Okay.
Cheyenne.
This is a question for Evgenia specifically. I can't remember which cohort it was that you mentioned. I believe it was Tetra River. Could you comment on how the different researchers accounted for internal exposure? For cesium and for strontium, they're fairly long-lived isotopes. So I'm just curious how the authors went from a continual dose rate to a single value for absorbed dose.
Okay, thank you for your question. Yes, let me repeat your question to make sure that I got your idea right. So you are asking about how the doses for the Tetra River residents being assessed, especially the ones from internal exposure.
That's correct, yes.
Okay, so okay. Okay. So first of all, yes, the internal exposure doses being assessed based on the several pieces of information. Of course, it was based on the individual behaviors. It also was based on the measurements of whole body counter of cesium 1937, strontium 90, and also potassium 40. That input data were used to reconstruct doses for the Tetra River cohort members. For the external doses, there were no individual measurements, and only the data of dose rate measurements were available. So the external component of the total dose from external and internal exposures represent just, individualized, or let's say, individualized dose due to external exposure. Did I answer your question?
Yeah, that makes sense. I was just curious if they did do any kind of whole body counting as well, so that helps for sure.
It
Thank
was
you.
used for, not all the 30,000 cohort numbers been measured on the whole body counters, but again, those who have been measured, and also the approach been used for the family members living in the same household, those who had the whole body counter measurements, this information could be used and extrapolated to some extent to the family members, meaning that they share the same ways of dieting, of using the river water. So that information could be to some extent extrapolated to the family members of the same household when reconstructing internal exposure.
Yes, thank you.
Other questions? Are there other questions on the website? How about from the group at large? Yeah, Dimitri, do you need to come up and... Thank you.
Question for Zdenka. Two questions actually. One is simple. Those three domains of epigenetic regulation, microRNA, histone modifications code, and the genomic DNA methylation. So did I understand correctly that in terms of transgenerational stability of these changes, do I understand correctly that DNA methylation is the most stable, then we have histone code, and then microRNA changes? Is that correct understanding?
Well, when I think about using mitotic transmissions, mitotic stability, I think you are probably right. The DNA methylation is really the most studied and best characterized, and indeed you can profile, you can sequence basically DNA methylation nowadays with the bisulfite sequencing, where you can actually create a SNP, and then you can, with precision, determine the number of or quantitative level of methylation on each at a single base pair resolution. That's so the methylation is can be established and can be monitored dynamically or whatever, even in single cell level. Now the histone modifications also, and we are talking about mitotic transmission from one cell to the other. So, and this is pretty stable in terms of, otherwise it's not even epigenetics, but it looks like DNA methylation is much more rigid, if you like, much more stable. The histones, while the non-coding RNAs can be more fluid, it's because it's kind of transcripts. And for some, even microRNAs would not be considered epigenetics for some people, because they are relatively, fluid, if you like, moving target, because depending on the stress, they might be expressed, high or lower level. Yeah, that's the first question. Yeah, so I think the DNA methylation is, because I think that this is the natural mechanism. So imagine you have all the 25,000 genes in all cells, and at one point you have to switch off the two-thirds of the genes. And the best way to switch them permanently is DNA methylation. So it's a normal mechanism, switching off the genes that are potentially dangerous or unwanted. Yeah. Second.
Might be more complicated. On the comparison between genetic and epigenetic mutation or changes, like an estimated de novo mutation, genetic mutation rate for human is about roughly one per 100 million nucleotides. It's a de novo mutation rate. So it's one spontaneous stochastic cells. Yes. So it's a DNA patch of 100 million nucleotides. Now I can imagine that in this long piece of DNA, you can have thousands of epigenetic alterations, yes, and almost infinite combination of them. For example, a single cytosine methylated can have a different effect if it's in combination with different other cytosines methylated, or histones, H3K27 methylated. So it's almost like a key, epigenetic key, which determines the effect, shutdown or activation of a gene. So with all this uncertainty and complexity of epigenetic alterations, do you think we're in a position to associate these very variable epigenetic changes and make connections to human detrimental and disease and generational, transgenerational changes? Are we in a position to start talking about this?
Yeah, I think you are right that the epigenetic events, spontaneous events that you may consider aberrant, are more frequent than genetic events. And in cancer, if you look on overall, you see much more, on average, much more epigenetic events than genetics. But as similar to genetics, there are many events that might not have any impact on the genes. You know, they might be in some kind of in a non-gene region, and the same for epigenetic. So what is important perhaps to keep in mind that if this event that happens in this stretch would not actually, even if one methylation, although this is schematic, one methylation event in the promoter will not silence the gene. So this event might not be equivalent. Let's say one event might not be equivalent to mutations, because one mutation in the coding region may completely truncate the gene and inactivate gene, while one methylation might not. So perhaps this explains perhaps more events, more spontaneous epigenetic events with perhaps less impact. But what is quite remarkable, what was done with this early generation of arrays that were quite robust as well, when they profiled the many cell lines originating from different people, from different even ethnical or racial, whatever groups, the methylome was remarkably similar. It's just amazing. You know, it's about differences because it's average. Often you are kind of averaging thing, because if you take blood, it's composition of of different cell types. But if you take blood from 1,000 people and do the methylome, regardless of their origin or whatever, you will see that they are remarkably similar. When you say similar, it's remarkably similar. I mean, you wouldn't. Profile of methylation, for example, methylation patterns would be so similar, and then the difference is sometimes 1%. So it's in a way, although it's often event, but if you put together, in a tissue, this is pretty remarkably similar, and so it is in a way you can establish what is aberrant. So,
that's interesting. Yeah. Andre?
Okay, thank you. Maybe I have a question about the origin of effects that we were discussing, and because we have seen that after the Hiroshima and Nagasaki bombings, and the radiation exposure took place within a split of a second, and you see transgenerational effects, weak, but you see them. We assume they are real. Is the origin a mutation, or is that kind of promotes people who are susceptible because of their epigenome, or is the effect because the split of a second exposure induces epigenetic changes? What do you think?
I'm afraid I cannot give answer, but I can speculate a little bit, just very briefly. The clearly genetic, the transmission of this disease or phenotype can be through the genetic. It does happen through the genetics. Whether this is entirely through through the genetics, yeah, through the mutations or whatever. Whether this is entirely through the genetics, I would not, bet because there might be a fraction, and perhaps there are, especially with more recent evidence, that the low doses of radiation, chronic protracted exposure with low doses has actually much more impact on the epigenome. And no, yeah, but for this particular case, imagine that this mutation perhaps affects in a gene that is involved in epigenetic regulation, okay, so-called epi drivers and so on. So I think that's I cannot say with a certainty whether this is entirely genetics. I would say that I would not rule out, but difficult to without maybe doing some studies. I don't know whether the studies. I must say I was not going. You probably noticed I did not go to many examples because there are many studies. Some good, some bad, some very limited on animals and so on that would look at the phenotype and very limited profiling of the epigenome. Some of them are not really transgenerational, as I said, just simply intergenerational. So I think there is more work to be done, I would say. But I'm convinced that this mechanism exists across different species. And use similar or similar mechanism might exist, may be used as an underlying mechanism.
Yeah, very good. And question? You had a question? Yep.
So I'm Ludmila, just for those who are online, and you mentioned about exposomic studies, and is they were also related with radiation effects, or you were just mentioning general one? Yeah, well, I know about exposom, but I was just interested if you were in studies with radiation also.
Yeah. So by definition, the exposome would entail the totality of exposures from the conception, not from the birth, from the conception to the to death. That's what the original definition of Chris Wilde. Now the people go to much more reduced, and they do not. They measure what they can measure, and they do omics. Otherwise it's. And I think original idea, the exposome concept is unfeasible. So that means you can measure everything that we expose to. But then you measure, for example, the first exposomics we were part of it, there was more focus on air pollution and water contamination. The radiation was not there. And I don't think it's in more recent either, but especially, but that's what I was arguing, that there is a need to incorporate. Yeah, exactly. Yeah. So, yeah, but then radiation you can measure. I mean, you can measure. That's good about radiation. You can. There are dosimeters, whatever. I don't know, but you are experts, But radiation's not all, but you can measure compared to some other, endocrine disruptors. Something that I don't know, night shifts, or whatever, things like that. That is very difficult to measure.
Okay, Dominique.
I think I found one question for both of you, so that's good. Only one question, two answers, yes. It's about the number of generations. So you were making a clear distinction between intergeneration and transgenerational, with the two first generations and afterward. And so what is your feeling? In the system at the time being, only genetic modifications are considered, and up to 2 generations only. Do you have a comment about that? And the same question for TRIO studies. From what you presented, I think most of them are able to do only the first generation. Maybe the semi-Palatinsky up to 3 or something like that. What do you think? Is it possible to extend it? Are there also populations able to go beyond 1 generation? So, same question.
Well, I think it's more. It's not. I mean, how do you, nomenclature, whatever. I mean, we have to agree. Transgeneration from one generation to the other, it is, transgenerational in a way, but I'm talking transgenerational epigenetic inheritance. So if you, for example, expose the pregnant mother, so you're exposing mother, you're exposing fetus, but you're exposing germline in the fetus already. So this effect actually is not necessarily transmitted. It's just basically the exposure actually already make impact in the germline of the fetus. So that's already F2, right? So if you go up to there, you say, okay, this actually has an impact on the next generation or 2 generations, but the inheritance is not whatever transgenerational inheritance, because inheritance means like the mechanism that propagates this, independently of the first hit. So that's maybe because we're talking maybe different, about different thing, but so I think that's, I don't know whether there is consensus on this, what you call transgeneration. That's what I don't know whether, maybe you can comment more.
Okay. Yeah, I think I tried to present, I don't know how successful I was, about the populations, especially the ones that experience the protracted low-dose exposure. And it means that it's not only their parents were exposed, received the dose before the conception, but also part of this F1 generation also received doses during in utero. And we cannot, decontaminate this effect. So for me, personally, I think it's extremely important to follow and include F2, that grandchildren of exposed grandparents and also children to the subject that could be exposed in utero, to continue to study, to get the better understanding and insights on the transgenerational effects. So what is possible, of course, we also saw that these populations are aging. The grandparents are already in their 70s. That makes also applies some limitations for future studies. So if to do that, we should act, sooner. That's, yeah. And the other thing, but the numbers, you still saw that the numbers are allowed. The numbers are allowed to get the group that would be informative for some conclusions, for some findings.
Okay. So can somebody tell us whether the transgenerational, in terms of the, can you consider this transgenerational? It is from, I don't know, it's just I'm talking about inheritance, and that's why it's important, because to rule out that.
Oh yeah, you're supposed you have to use the microphone.
Yeah, so I don't know whether somebody can, in this field you are working, I mean, to me, it's just about the kind of, agreeing on what we consider, transgenerational.
We're going to talk about it in the groups, but thanks. We're going
it does not actually, minimize or whatever the importance of the, impact on the generation on the, so it's just about inheritance.
We'll circle back on Thursday, and we're going to break for lunch, but you get the last comment, but make it short.
Okay, well, short 2 comments. It's actually one study, but very quickly. One study I read in Russian, it was PhD. They were estimating effects, can be duration of effects until 7th generation. But about your comment, Evgenia, apart of in utero exposed, actually all these people who are after birth, they are living in contaminated areas, so they also receive external exposure. So here, it's even more difficult to separate.
All right. So, do you want to say something or?
Well, yes, just a short comment on this reprogramming. In fact, when the sperm matures, the histones are replaced by protamines, and that's kind of reprogramming as well, or removal of these signals. And it would be quite interesting to think, and perhaps we discuss it in the group, about the kind of, let's say, selection of mechanisms that can reduce the genetic effects as well, or act in the like the oocytes that can repair actually sperm DNA damage. So there are these different steps that can impact the process, and it would be interesting to know if they are similar in humans and in the experimental animals.
That's just very briefly. That's important. I mean, because in the textbooks we learned, in spermatogenesis, the histones are removed by protamines, and that's it. Now the high resolution studies show that in mouse 7%, in human 4% of the histones are not replaced by protamines, and this could be a memory mechanism. Similar to what, and actually that was a relatively recent study. So I think that's whether this can remember still certain event during embryogenesis, and then further for the, could be transmission mechanism. So I think that's that. So whether female, whatever the oocytes provide, whether this could contribute to repair, it is possible. I mean, as you know, after fertilization, there is an active demethylation, and there is a difference between paternal and maternal. There is delay for maternal. So so that's very interesting. Why maybe there is this little bit about the dosage and the imprinting and so on, and little bit struggle whether between the dosage of different genes. And that's imprinting is really important because, that's what we can talk about, of course, evolutionary meaning of the imprinting, but that's the one mechanism, and maybe repair is also part of it.
Yeah. All right, we can talk over lunch, but we need to be back here at 2:15, right?
Good afternoon, everyone. I think we had a nice discussion in the morning, and we realized that there are many issues to discuss. I hope I'm not throwing more complications into the topic and discussion, but I struck out confounding because we don't have the proof yet that there are confounding factors. So I will come back to that point later. So I would like to speak and point out some of the factors which influence effects of radiation in animals and in humans, for example. It's just throwing ideas. It's a concept, and I don't have any. I'm just highlighting the facts from published data. And we all know about radiation effects on embryos and offspring. I don't need to go into details. We also know that germ cells and developing embryos may be sensitive or may have, may be susceptible to radiation effects. And there may be other environmental factors which may influence the radiation response in germ cells as well as developing embryos. This is a nice, graph showing different stages of fetal or embryonic development, which may have differential susceptibility to radiation or any other types of environmental toxicants, for example. Okay, so this is taken from last year's publication. And why I am doing this, and it has been 30 years since I have been working on the topic of in utero exposures to X-rays and diagnostic ultrasound in developing embryos. I mentioned this in our first task group meeting while I was doing my PhD with Professor Uma Devi. I submitted my thesis in 1991. Incidentally, my supervisor was with the task group 39. This was the report ICRP publication 90, published in 2003. And as you see here, there are great experts in the field in that particular committee. This year, she celebrated her 80th birthday. We wrote an article about that, her PhD student. And this was the beginning. And then 1990s were the time where low-dose studies are not favored because adaptive response was coming up like this. And any journals in radiation field, if you submit low dose radiation, definitely there will be a lot of questions asked. So I was doing the diagnostic ultrasound as well as diagnostic X-rays in combination. Okay, so I used a diagnostic instrument at that time. Probably nowadays the instrument might have improved in resolution as well as in its effect. So I used mouse model here. 10 minutes exposure. These are the parameters used for ultrasound. I know I'm going a little bit away from ionizing radiation, but believe me, this is very relevant. This is very relevant for our radiological protection, because I wrote a review on this in 1995 claiming that we will not have a control population in the world when we want to study the ultrasound effect, because every embryo would have been exposed to diagnostic ultrasound. Okay, so I did mouse work, and we studied a lot of growth parameters, learning, memory, locomotion, etc. All are postnatal effects. As you see, initially I published in Radiation Research, and I have to switch to other journals, teratology and neurotoxicology and teratology, right? And then the interesting part here is I did a combination exposures, diagnostic X-rays and or ultrasound. Okay, so that has a synergistic or additive effects in the embryonic development and postnatal behavior, for example. So when we looked at the mechanisms of ultrasound effects, exposure to ultrasound will increase the temperature. This was found to be between 0 to 2.5 degrees Celsius. Okay, for mouse, in my studies, it was about 1.5 degrees Celsius. It depends on the time, duration of ultrasound exposure. And the interesting part here is that even though the temperature is high, the entire embryo is getting exposed. So that's interesting part here. In the review published in 2007, it was pointed out that thermal rather than non-thermal mechanisms are more likely to induce adverse effects in utero, and the low probability, but under some conditions it can be high, because if you have repeated exposures, then you have increased temperature exposures as well. And that led to me to study heat effects on embryos. Okay, so this was the experiment done side by side with my PhD study, exposed to hypothermia, 39, 40, 41 degrees. So there were developmental effects. And this review I found out just 2 weeks ago, where influenza and there is an association between influenza and congenital anomalies. This is a systematic review. And in this particular study, they have also pointed out that neural tube defects, cleft palate effects were found in children who were born to mothers who experienced influenza during pregnancy. Okay, so that highlights that heat or temperature may have some role in using congenital anomalies. And there are several other factors such as microwaves, EMFs, for example, microgravity, all can increase the temperature in the body upon exposure. And this particular review, case control study was published in 2011 by Preetha Rajaman, who is one of our committee members. And here you see that early exposure to diagnostic radiation, it can be either preconceptional or during pregnancy or even neonatal exposures. And we considered the following variables as potential confounders on the basis of possible association with childhood cancer, that is maternal age, smoking, socioeconomic status, pregnancy order, and all sorts of confounding factors. But they narrowed down only to few of them here mentioned: birth weight, and then maternal age, and then the age, sex, and study region. So they excluded all the other confounding factors. I think most of in our radiation studies, we exclude all the confounding factors in our analysis, and then we want to focus on only radiation effects, right? And this study eventually identified that the doses which are being in the diagnostic instruments lower than those doses can have an influence on childhood cancer incidence. Okay, so that was the conclusion from this paper. And this is again a combined exposure, diagnostic radiation and ultrasound. Either it can be postnatal or in utero exposures. So that's only one study I found which is on human epidemiological studies. And then I'm going to highlight some of the other factors involved. Complex exposures in the environment. We have heard all the studies about radioactive substances in the environment. And then I highlighted some factors such as heat and other sources. Residual pesticides, this is very relevant for low and middle income countries where women work in the field and they get exposed to pesticides when they are pregnant. And of course, the effects may depend on nature, magnitude, and possible biological significance of these factors. And when we did a search on PubMed using different keywords, here you see there are 97 publications in the last 15 years which were on transgenerational effects. And when I combined that with the other factors, environmental factors, we still get 171. We need to further analyze these. I haven't done that yet, but we will be planning to do this analysis in the recent future. And when I went through one of the reviews published in 2016, exposure to different environmental chemicals, when this group analyzed the different chemicals in cord blood or maternal blood. As you see here, there are several environmental toxicants which were present in the human blood, actually exposed to environmental toxicants. So from this review, the authors concluded that birth weight was consistently inversely associated with exposure to pollutant mixtures. Chemicals not showing significant associations at single pollutant level contributed to stronger effects when analyzed as mixtures. So this is what I think it's important, because when radiation exposure combines with other environmental toxicants, maybe there are more heightened effects. So as I mentioned earlier, I'm going to throw one by one. So I started with ultrasound, heat, and now smoking and radiation sensitivity. Of course, this is done in a healthy population, but the questions asked here is whether smoking during pregnancy can increase the sensitivity of radiation exposure. That's clearly important. Any increased susceptibility of the germ cells, fetus from couple who smoke. This can be preconceptional exposures. And there were isolated studies published in the literature that UV radiation increases sensitivity to pesticides. That's the one point I mentioned earlier. Synergistic effects of UV and pesticides on both cumulative reproduction and population growth rate. Of course, this was done in lower organisms. As we have seen in the morning, there's some of the experimental studies were done in lower organisms because you can do multi-generation study in a short period of time. Again, another study. I think I'm running out of time. So it can cause additive effects on radiation-induced mortality, more likely to induce sublethal changes. More evidence are generated from lower animal models. So this is again in an amphibian model where larvae were exposed to combined exposures to pesticides and then UV, for example. The interesting part here is that exposure to pesticides can alter the immune response. And this may lead to increased susceptibility to any other exogenous challenges. Okay, so when you alter the immune response in the embryos or in pregnants, any other exposure can lead to heightened effects as well. And now coming back to some of the lifestyle factors. androgens and estrogens can decrease radiation sensitivity. There are some reports available. They can modulate radiation sensitivity. Metabolic disorders, gestational diabetes, for example, may have some influence in radiation response. And we know that pregnancy alters endocrine profile, and thereby it can modulate the effects of radiation when they were exposed. And I question here, this can be a contributing factor for altered radiation responses. I didn't mention here whether it's sensitivity or resistance, because it can be either. So finally, we all know this, but I have highlighted some of the factors which may contribute to the response to germ cells, whether it's testicular cells or ovarian follicles, for example. These are some of the changes, some of the lifestyle factors, as well as environmental toxicants. Eventually, embryos will have poor functional competency, genetic and epigenetic changes, chromosomal abnormalities, ultimately leading to defective embryonic development. And pre-exposure to any of these conditions, whether they will increase the susceptibility to radiation-induced damage, this we need to consider. Okay. So finally, I would like to list out some of the factors which may influence radiation effects, as can be seen here, which I have highlighted, taken from the literature actually. Alcohol consumption, another one, and these are some of the consequences of exposure to any of these agents. Okay, so potentially these factors, exposure to these factors may be relevant for radiological protection as well as for risk estimation, and that's the concept I'm going to propose here when we come up with the policies against radiation protection and risk estimation. And finally, thanks to my collaborator who does a lot of embryonic studies. He's an expert in reproductive sciences. And of course, I had to acknowledge my daughter, who is currently an epidemiologist doing PhD with Nagasaki University. And she asked me to strike off confounding from the title. And thank you very much. Sorry if it is a little bit out of radiation topic, but I thought it's relevant.
Yeah, thank you, Prakash. We've got a whole session on discussions, but I mean, are there any specific questions to Prakash? For sure.
I left out the sociological aspects. Okay, I know that's one.
Okay.
No, actually, we are mentioning heat, yes. But apart of heat, we are speaking about radio frequencies effects. Yeah. So it's also and about light, I just wanted to maybe to know, because some colleagues from East Global, they also did study about blue light, light from mobiles and from screens. This blue light also was associated with developing cancer. So not only light of heat, but also different types of light.
Yeah,
just comment.
I have left out some of the factors, but I think there are. I know that I realize that psychological, factors may influence as well. Yeah.
Okay. Thanks. Any specific questions to Prakash? Otherwise, we've got the general discussion. Thank you, Prakash. Thank you. Okay, so the second talk this afternoon is Svetlana Sotnina. Isn't it? Yeah, I'm going to say, Eric, you've changed dramatically, which is pre-recorded. Gosh, my heart. Yeah, okay. So let's see. Let's see if we can get it on. Thank you.
Good afternoon, dear colleagues. I'm honored to present my report here. I express my gratitude for this opportunity to the organizing committee. Let me introduce you to the result of our pilot study. This is a retrospective analysis of congenital malformations in all the 1,000 children under 15 the quota was then being borne by mothers who had accumulated preconception occupational doses of external gamma irradiation. Congenital malformations are characterized by etiological heterogeneity. In this pilot project, we try to take into account all available potential factors for the development of congenital malformation in the cohort of descendants of the Mayak Production Association workers. The Mayak Production Association, which began to operate in 1948, is the first Russian nuclear cycle enterprise. During early years, particularly when the technology was still under development, Mayak workers could receive substantial radiation exposures from external gamma radiation and alpha particles from incorporated plutonium. Our research aim was to analyze congenital malformation in children born by female workers employed at Mayak PA who had accumulated preconception doses of external gamma irradiation. We analyzed the class 17s or the ICD-10, and we concentrated only on such cases when the malformations were first diagnosed in children younger than 15. This epidemiological study is based on registries which are created in our institute. Mayak workers cohort includes about 26,000 workers initially employed in 1948 to 1982. It should be noted that 25% of them are female workers. Dosimetric characteristics of parents' occupational irradiation were obtained from Mayak workers' dosimetric system. We applied values of accumulated preconception external gamma irradiation on ovaries. To make a comparison, we also give values of an equivalent for an observed external gamma irradiation dose on the body surface, HP10, and preconception observed doses of external gamma irradiation on the large intestines. Azovsk Children's Health Register is a computer database which contains personal, medical, and social data taken from children's outpatients cards. Azovsk is a closed town located in the vicinity of the nuclear enterprise. We applied the following criteria for study group. A child should be born in Azovsk in 1949 to 1969. A child's mother was employed at Mayak PA and had an accumulated preconception dose of external gamma radiation on her gonads. A child's father didn't have any accumulated doses of preconception occupational radiation. He hadn't moved to Azovsk from territories contaminated with radiation, and he hadn't previously taken part in liquidation of any radiation disasters. Finally, our study group was made up of 238 children. Control group was created by case control method, allowing for sex, year of birth, parent's age at the moment when a child was born. We applied the following criteria for control group. A child should be born in Azovsk in the same period. A child's parents had never been exposed to any occupational and ecological radiation. As a result, control group included 932 children. We used the descriptive statistics, chi-square criterion, and Fisher's exact test, odds ratio, and factor analysis via basic components technique. The highest doses were detected among female workers employed at Mayak PA during the first years of its functioning. A maximum dose of external gamma radiation on gonads reached more than 3.5 gray among irradiated mothers. An average accumulated dose of external gamma radiation on gonads amounted to 373 milligrays. We should note that there were data on irradiation in utero of 76% of children, with an average dose amounting to 25 milligrays, as mothers were exposed to radiation at early stage of their pregnancies. High level of preconception irradiation of female workers can be explained not only by imperfect production technology, very limited time of production schedules, and the absence of any experience in working with sources of radiation, but also with the concepts of permissible radiation exposure at production which existed at that time. Most children were born within mother's radiation range up to 100 milligrays. However, each 10th child was born by a mother with an accumulated external gamma radiation dose on their gonads being more than 1 gray. There were some differences in the structure. CM in the nervous system and respiratory organs, 23%, prevailed among children born by irradiated mothers, while CM in the musculoskeletal system prevailed among children born by intact parents. However, we didn't reveal any statistically significant differences in CM frequency. Odds ratio value in the compared groups showed there was no significant correlations between mothers' occupational irradiation and malformations in their children. In order to reveal any latent factors which explained correlations between any examined variables, we performed a factor analysis. 4 complex independent factors were spelled out among 15 features in the group of children born by mothers employed at Mayak PA. The total share of the explained dispersion amounted to 62.5%. The most significant factor was that related to mother's preconception irradiation, as it made the greatest contribution into the dispersion, 21%. Factors loadings of such variables as those on gonads, those on the large intestines, and those AP10 were also high. The second factor included gestations, age of a child, multiple pregnancy, and parity of delivery. The greatest loading in the third factor was represented by mother's obstetrician case history, a number of previous pregnancies, and abortions. The least contributions in the dispersions was made by the factor about bad habits of mothers, alcohol intake, and smoking. It is interesting to note that after the variables which described mother's occupational preconception irradiation were excluded, factors solutions among children born by female Mayak workers became similar to that existing in the control group. Thus, our pilot retrospective analysis of congenital malformation showed the following. There were no statistically significant differences in CM frequency between two groups. There were some differences in CME structure, such as prevalence in CME of nervous system and respiratory organs among children born by irradiated mothers. We didn't reveal any chromosome pathologies in groups. The dose interval of maternal doses of external gamma radiation at which malformation were observed in the offsprings was 1.9 to 1,600 milligrays, with average dose being equal to 300 milligrays. And factor analysis indicated 4 factors characterizing mother's preconception irradiation, offspring antenatal period, obstetrician gynecological case history, and bad habits of mothers. In summary, in this pilot study, we try to quantify the factors that may be important to control confounding or to provide insights into effect modifiers. We regard our results as preliminary, and we are going to continue our study for final conclusions about the features of the congenital malformations in the offspring, including dose response study. Thank you for your attention.
Thank you, Svetlana. Is she online, or do you know? Just.
Yes, I'm here.
Oh,
I'm
good.
glad to see you very much.
Good. Thank you. I wasn't sure if you were there or not. Thank you again, Svetlana. Now you can hear us. Now, I don't know if you heard what I said after the first speaker, that we do have a general discussion session, but I guess it's getting on in time for you there. So, but are there any particular questions for Svetlana now following her presentation? Svetlana, are any of these results published yet, or are these just preliminary results that you're showing us, or what?
Yes, our results is published in the Journal of Health Risk Assessment, and we are going to conduct the next step of our research. We are collecting now more large group of our following offspring, and we hope that our next research will be more reliable and more relevant to this task which you are searching, that you are considering. We hope that our future research will be more complete. Thank you.
Okay, yeah, thank you for that. It's looking at those doses and the numbers. It's clearly, you know, as ever, the early MIAC workforce is potentially very informative. Will you be available for the later discussion session?
Yes, of course.
You will. Okay, I know it must be getting late over there. Okay, so thank you very much indeed. We'll move on to the third speaker. You got it right this time, Eric. It was Eric Grant from RERF. Over to you, Eric.
Thank you. Thank you very much for the opportunity to speak. I'm actually a pinch batter for Bob Ulrich, who is actually a member of the committee and of the group. I'm not, but I was asked to come in his stead. And so you lose some biology, but you gain an epidemiologist. And I didn't have a talk prepared for this, but I was asked by Dominique to please give a little history on the Radiation Effects Research Foundation second generation cohort, a little bit about how it came about, and also what the current status is in terms of our research and our materials. So that's what I'd like to talk to you a little bit about, and we'll fire away. This background, you guys all know it, but But the F1 study, the Children of the Atomic Bomb Survivors study, was actually the first study that got underway at ABCC, the forerunner of RERF. It's interesting to think, I mean, the lifespan study and whatnot are very long-term studies, but they actually didn't get organized until the mid-1950s. And the first study that actually got off the ground at ABCC were the children of the atomic bomb survivors. So it's actually the oldest study, and was because of the fact that it was unknown what would happen in the children of the atomic bomb survivors. And there was great fear around the world regarding what kind of effects may be found there. So that one got off the ground early. And Ritsu talked a bit about this earlier, but it's a great story. So at the time of the bombing, just after the war ended, food was rationed in Japan, and rice was rationed in Japan. And if you were pregnant, however, you got an extra ration of rice. And you had to go to a city office and ask for that ration. And so the ABCC clerks or whatever set up a table next to the window where women would have to come in and ask for this rice. And they would say, oh, congratulations on your pregnancy. We'd like to follow your birth, please. And the nice thing about this is that 90% of all pregnancies were tracked in Hiroshima and Nagasaki between 1948 and 1953. And exposure status was known early in the pregnancy, so there was no recall bias in terms of trying to figure out what the exposure scenarios were. So the physician would visit the home afterwards, and 76,000 births were tracked. And ABCC was run by the US military early on. They had their own fleet of jeeps. They had their own fuel depot. They had their own mechanics. The whole system was amazing. And of course, there's no computers, there's no telephone. The roads are in bad shape, so the jeeps would be crawling over the roads and trying to get to these different homes. And this is how this all happened in the early years. And then they would go to the home and actually do an examination on the child. They'd have these teams, a driver, a physician, and an assistant would go out and examine the babies and write down what they saw. So Ritsu talked about this earlier. Untoward birth outcomes was this early study. The hypothesis visible malformations and early death in offspring would be more frequent among the irradiated. And so they're looking for visible malformations or early death. And Ritsu gave the talk this morning. I wasn't sure of the timing. Then after that was finished, and ABCC got organized with the lifespan study and the adult health study and the in utero study. The F1 mortality study was also started as a fixed cohort at the same time. And about 75,000 children born to atomic bomb survivors and not in city parents. These are people that were registered as residents in the city of Hiroshima or Nagasaki, but for some reason weren't in the city at the time of the bombings, were also included. These children were born between 1946 and 1984. Follow-up between birth and age of death. Exposure is paternal or maternal gonadal radiation doses. Outcomes are cancer incidence or mortality. And this is from a study that we published in 2015. This is kind of an interesting slide. The yellow indicates when the birth outcomes, that 1948 to 1953 study was done, when we're actually doing the active follow-up for women that are coming into the city offices. But after ABCC got organized and we had a master list of all the people who were in the city at the time of the bombing, then you could go to city records and look for births, names of births, of who was born in the cities between 46 and 48, or between 48 and later, and match the parents' names with the master list of who was in the city at the time. So in fact, by matching city records, we could go back to 1946 and find out who was born to an atomic bomb survivor early on, and that was done again. In 1958, the actual F1 study, mortality study, gets organized on its own and follows out. And after that, anyone who was in the lifespan study and had a child was then added to the F1 mortality cohort as well. And so we've got these additional births happening. And then finally, in about 1980, the women are about 45 years old. Then naturally, there's no more births happening. So you've got this, the entire lifespan of, or entire age range of mothers exposed or women exposed to the atomic bombing, either very young or at the age of when they might have a pregnancy. So you've got these women having pregnant births throughout different ages of exposure. These are some results from the F1 mortality study published in 2015. At that time, the median age of follow-up was 53. The mean age of children still alive was 53 years old, so quite young still. Number of disease deaths also quite small, 5,000 at that time, 1,200 cancers, 2,900 non-cancers, many of those happening early on due to pneumonia and other kinds of infectious diseases when medical wasn't great. And then quite a few external causes as well at that time. And maternal exposure hazard results for cancer or hazard ratios for cancer or non-cancer. Paternal and maternal exposures, nothing, we didn't find anything significant here. So historical results, this birth defects study, 1948 to 1953, not significant findings, but this reanalysis published by Dr. Yamada has some suggestive results at that time. You heard about that this morning. And then there were several other studies, a sex ratio, a cytogenetic study, and a biochemical genetics study. None of these have significant results. We're currently in the process of designing a whole genome sequencing study of the F1. And this will probably be the, I don't know, our most definitive type of results to try and come from this whole genome sequence analysis. And I can just talk about that for a moment. It's currently under design. We're spending a lot of time talking with our stakeholders to try to gain their understanding. The study is fraught with social concerns. The actual survivors themselves suffered stigma due to their exposure. And so far we don't see anything in the children. But if the results were to indicate that there were hereditary effects from radiation exposure, we would reopen a wound that's really begun to heal. And so there's a great concern about that. And so we're trying to be careful about it and let people understand what we're doing, why we're doing it, and what we may learn. And I would say I've been in a lot of those meetings, and the feedback's actually very positive. People want to have their results from this tragedy be used for something that's positive for humans. And I'm actually quite impressed with the attitude that I see in those rooms. So we're working to try and get through those stakeholder committee meetings. And I think we should be done in sometime this summer, we hope. Up to 1,000 trios are possible, although we do need to do long read sequencing or very deep coverage sequencing to try and look for structural variations. And of course, that adds to the cost in terms of trying to do deeper sequencing. So the more sequence, and of course, everything requires a trio, a mother, a father, a child, just to get one result. So it's expensive, and we're trying to figure out how to get that done. SNPs are easier to detect, but they're probably not as common, we don't think, based on what the Chernobyl group has recently published. So, we want to do these long sequencing reads. In addition to the whole genome sequencing study, we've got what we call the F1 clinical study, or FOX. This is from the mortality study. A subset of those persons come into our clinic every 4 years, and we do a full medical workup on them. Blood draws, urine draws, EKGs, all the things you might do in a standard screening for general health check. That's based on the F1 mortality cohort, about 20,000 male questionnaires in 2000. 10,000 came to the clinic, and now we're following them up every 4 years. The mortality study continues. Cancer incidence has become a bit of a problem. We used to have local registries in Hiroshima and Nagasaki. Japan has recently moved to a national registry for the entire country, which you would think would help us because now we could track cancers across the country. But the problem is that to find the people, you need an address and a current address for people. And a lot of the follow-up that we do is actually passive in terms of we don't know where people are. We're just watching for their names to show up on a registry of people getting sick. But Japan has a lot of common names, and unless you can localize that person, you're in trouble trying to figure out whether or not that person is our person. And so what we can do now is follow cancer incidence carefully among those who are coming to our clinic because we have close contact with them, we know their addresses. But the larger cohort probably is going to be best suited for mortality, unfortunately, in the near term. So the whole genome sequence study is coming up. General access to the FOCS data may be possible, but is not easy or simple due to a lot of these social concerns that we have, as well as the fact that that study is only in its third round of follow-up, and we haven't published yet on what we're finding in the FOCS study as a longitudinal study. So that's going to have to come first. F1 mortality and cancer incidence access to data are easier than the clinical data, but RERF is struggling right now with a lot of data sharing issues, and it's something that we're working through as best we can. And pretty much that's what I wanted to talk to you about. If there's any questions, I'd be happy to answer them.
Yeah, thank you, Eric. Very, very interesting. Always interesting to hear what's going on at RERF. Very important set of studies. Interesting. Japan doesn't have any national identification number of some sort. Wow, that is interesting. And of course, anyone involved in the field, ethical issues become more and more difficult for these things. So I fully appreciate that. I guess the F1, you're now moving into the multifactorial arena as people age. Any indications of what might be happening there?
That's not published yet, but there's no positive results. And actually, there seems to be some, if I can say, perhaps sort of negative results in terms of these folks may be more health conscious. They're coming to our clinic and they actually seem to be doing somewhat better perhaps than the general public would be doing. Nothing radiation related, but just tends to be a very healthy cohort at this time.
Yeah, thanks. That's very interesting. Just as one more specific question.
Thank you. Very interesting results. I was wondering if there is information about C-section versus vaginal birth in this cohort and in other F1 cohorts, because we know that these newborns, they differ in the microbiome, skin and intestinal microbiome, which plays a key role in the immune system development and maturation, and immune system plays a key role in protecting against the cancer onset. So is this information available, and is this considered as a confounding factor, or?
I don't know the answer to that question, but C-section would be rare, I would think, in Japan prior to 1984. And certainly prior to, say, the 1960s, when most of the births were happening. So it is possible that certain children were born with C-sections later. I don't know of a variable that we've got, but it might be something that we could dig into. But my guess is that there aren't very many C-sections in this cohort. That's my guess.
Yeah, thanks. Oh,
because of the age of atomic bomb survivors and their children, probably there is an effort ongoing on the F2 cohort. Could you comment on the status of this?
Yeah, so far we haven't tried to do anything with the F2. It's a question we get often. Based on the F1 study that we've got with the FOCS study, I could see that we could have a natural extension to their children. But as of today, there's no such discussion.
thank you. Yep, thanks very much for that. So our final talk in this session before we move to general discussion is Augusto. Here.
Thank you. So I thank the organizer for inviting me to talk a little bit about the dosimetric aspects and uncertainties relevant for task group 121. So I thought to share a little bit my thoughts of what would be interesting to investigate and to analyze in the work of task group 121. And I'm happy that already this morning other speakers mentioned the importance of reliable and, if possible, individual dosimetry, because dosimetry is one of the relevant parameters, of the relevant variables upon which against which you evaluate the risks and the effects, and also for a correct interpretation of the confounding effects or non-confounding effects or the other effects which are available. And so it was interesting to acknowledge that in the current reports you read that most of the evidence or the information that is now available is controversial, or there are some contradictions, and sometimes this is due to not proper dosimetry or imprecise dosimetry, and that you might expect from studies in humans or from cohorts in humans where most of the exposure situation may be unknown. But this is also valid for in vivo studies or animal studies where the conditions are more or less controlled. And in this aspect, I was interested, I find very interesting, at the Radiation Research Congress in Manchester, there was an interesting poster about a survey showing how in the majority of radiobiological studies there were imprecise or incorrect reporting of dosimetry and of physics, which led to what the author called a little bit dramatically to a reproducibility crisis of the radiobiology study. But of course, this is an issue that is for us of interest, and I think this is one issue that should be interesting for our work. And a part of that, there is also the issue, which are the doses that we are using for the benchmarking. So in the terms of reference of the task group, we have, as in this workshop, these both the preconceptional and the postconceptional effects. And of course, for the preconceptional effects, you have the doses to the gonads, but as you remember, the title of my presentation, it's about the dosimetry and the related uncertainties. So how is an uncertainty on these doses, for example, related to the uncertainty to the correlated effective dose? Maybe doses to other organs also relevant. And in the case of post-conceptional effects, through the exposure of embryo and fetus, in general, you assume for embryo, you approximate with uterostar dose. For fetus, you may have specific models. You may have also the possibility to calculate the dose to a single organ of the fetus. In the last years, in the recent years, from the latest publications, groups in ICRP or related with ICRP or parallel from ICRP has developed dosimetric phantoms for the pregnant women that were very detailed. They allow to make the calculations for different organs, and they are very useful. They might be very useful to be considered. And I find interesting in the presentation of Evgenia this morning, she mentioned about her cohorts, the issues related to the dose for the incorporation of radionuclides. And this is something I wanted to a little bit elaborate more on. If we consider incorporation of radionuclides is per se a very strange and complicated issue, also considering an acute exposure, so not a chronic exposure that's like the one we have in the cohorts, but simply an acute exposure. You have incorporation of some material which stays in your body. It may stay for years, depending on the physical and biological consideration. It leads to a non-uniform irradiation in the body, depending on which organs the substance goes. So for iodine, for example, we know it goes preferably in the thyroid. Cesium is more or less distributed in homogeneously in the body. Strontium goes preferably in the bones. So we have a different, so non-homogeneous irradiation, which changes with time because also the concentration in the organs changes with time. And we know that the effects of, and the sensitivity and the sensitivity and the producibility of the effects depend also on the gestational time. So this is something which is more or less complicated to differentiate if you have a chronic inhomogeneous exposure. You also have to consider that the embryo or the fetus is not only irradiated by the activity which is in the body of the mother. Some activity can also be transferred from the placenta into the embryo and the fetus itself. So you have activity concentration in the fetus that may be also inhomogeneous, distributed in the different organs, which lead to an additional contribution to the dose. And when this activity is in the body, it remains also after the birth. So you will have an additional contribution to the dose after the birth that should also be taken into account. And on top of that, it may be that some additional activity comes from the maternal milk, if there is a transfer from the maternal milk. So you see, it's a very complicated issue, which makes very difficult to actually have a correlation between which effects I want to see and to correlate it with the internal dose. And as I said, we have these nice models. With these nice models, we can calculate the dose to the different organs, combining that with the biokinetic models. We can also try to make a kind of resolved calculation of the activity. But of course, here we have the uncertainty. And can we calculate an individual dosimetry, which will be the goal under this uncertain consideration. And so just to finalize, in the terms of reference of our task group. We have these to discuss separately preconceptional and post-conceptional effects of radiation and related morbidity and mortality, which by internal contamination, on the basis of what I've said before, might be a problem. In any case, I think this is one of the interesting aspects where in the work of our task group and in the review of the available literature and on the available information, we might have some interesting work to do. And I hope we can have also time during this workshop to elaborate and to get input on that. So that's the end of my presentation. Thank you.
Thank you, Augusto. Any specific questions for Augusto and his presentation there before we get into the general discussion? No, sorry. I mean, dosimetry, I think is one of the an important aspect, it's always interesting that if we look at the occupational exposures, those exposures that are going to be potentially most informative are those in the early years, where of course exposures tended to be high, particularly in places like Mayak, but not only Mayak, but Sellafield and some of the US sites. But when you go back that far, that's when the doses become more uncertain. There are missing doses, undoubtedly, neutron doses, some of which will have been completely unrecorded, but will have been quite significant. I mean, I know that from dose reconstructions. This extends to photon doses as well, because of the nature of film badges and the so-called missing doses. And then, of course, the problem of internal doses, which is even more of a nightmare because, at Mayak, for example, where plutonium doses, plutonium intakes were substantial in the early years, but monitoring only started taking place systematically in the mid-1970s, for example. So, and then only covering a limited number of workers who are so exposed. So we have to tackle, these sort of a multitude of dosimetry uncertainties to get to that. I don't know if you wanted to respond to that.
No, I completely agree that the issues of dosimetry is that because of the many situations at the RAND, at the border, that the best that you can do is to identify and quantify the uncertainties and to see how these uncertainties allows you to make a reliable evaluation or assessment of the effects and risk. I think that's the most that we can do from the dosimetry part, apart from maybe where you have the planned experiments, then to try to improve the planned dosimetry in order to have not to risk this reproducibility crisis, as what is called in the poster.
So, yeah, well, it doesn't matter. I mean, oh yeah, okay. So thinking about this a little more, we can think forward instead of backward, and the badges are better for workers. Also, our pregnant women today are older on average in developed nations. So, like I may talk about if I get to it, 1 in 1,000 pregnant women in developed nations get cancer. And most of those cancers are breast cancer or cancers that need radiotherapy during their pregnancy. So they're going to expose that fetus to radiation in one form or another, and to get worked up for treatment decisions during pregnancy. There are now guidelines, at least in the US, that they can receive PET is now considered, PET-CT is now considered appropriate for them, for pregnant women, because the dose to the fetus and to a woman, like their breast, is low, relatively low, and life-saving. So I don't know if you want to comment on that. And the second thing, they can also get colloids if the center that does the imaging knows how to do it well and optimize in the pregnant woman. So these are important things, like for melanoma, that they can get that kind of staging for that particular cancer. So anyway, it would be a way to understand and put registries out for these women, because we don't have that information. It would have to be an international registry for these women, and also for young children who, to correlate with the young children who survive cancers, which many do, most do.
So I agree, and I think I remember this morning I saw there was in a presentation about the different cohorts which are considered radiotherapy patients, and just to make a small example, we get sometimes information or calls from pregnant women which has been exposed unexpectedly, so maybe they get some radiotherapy, and then they find out that they are pregnant. And also there, for us a little bit, the question is, which is the best dose I have to calculate in order to give a reasonable estimate of the risk. But I agree completely, and this is something we are also trying to do in Germany, to get a register for all these people which are exposed, so pregnant women which are exposed for medical reason, because on one side you have a rather accurate dosimetry. Yeah, although I remember again in Manchester an interesting presentation showing that these out-of-field doses for pregnant women so these programs were not as accurate as they could be, but in the meanwhile we have some improvements in the software, and with this new method of calculations we might improve also this calculation. But of course this could be a good cohort that can be included in order to improve a little bit our knowledge about it. Yeah.
Okay, I mean, we can open out the discussion now. I think, and as I say, I think it was in one of the Ethel Gilbert's papers, dosimetry is key for epidemiology, and for sure, and this. This is a really difficult problem to grasp, because the most informative stuff is the most difficult, and we have to have in the occupational exposures, for example, dose reconstruction is one way to go, and you really have to look very carefully at these early doses. And as I say, it's the early doses which were the highest doses and which were going to be the most formative, which are going to be most difficult. And you're going to have to attack this issue to really make sense of what's coming out of these studies. Please contribute if you any of the issues that have been raised in this session. But I just to concentrate on one aspect, it's the interaction between radiation and other factors that are important for cancer and all sorts of other disease, including hereditary disease. I'm sure it's just a question of reminding you, but it always is something that interests me, in that there's implicit in in publication 103, for example, is that there is, for almost all cancers, the implicit assumption that there is an interaction between radiation and the major risk factors. And that comes from the way that the risk is moved from the principal source of information on radiation risk, which of course is a lifespan study of the Japanese atomic bomb survivors, and how you move that risk around to other populations. Now, if all populations had the same background rates of cancer, particular types of cancer, there wouldn't be any problem. But of course they don't. And ICRP publication 103 gives us an example, stomach cancer. And stomach cancer in the mid-20th century Japanese population was about, I think that 103 cites a factor of about 12. The stomach cancer rate in the Japanese population is about a factor of 12 higher than in an equivalent North American population, for example. So it very much matters as to whether you just move the excess absolute risk, the additional risk on that you get from the Japanese atomic bomb survivors. Do you take that and add it to, for example, a North American population? Or is it the proportional increase in risk in the Japanese population that you move around? And it matters a lot under those circumstances for stomach cancer, which they give as an example, as to whether you move whether you add the risk or whether you multiply the risk. In ICRP, in the current recommendations, for most cancers, it's 50-50. So you move 50% of the absolute risk, the additive risk, and 50% of the proportional risk. So implicit within there, because you've got the proportional risk, because it does matter what the background risk of cancer is, implicitly, you are assuming that there is an interaction between radiation and other factors, the major factors that cause those background rates. It's already there. But of course, you do 50-50 because you're largely ignorant of the way radiation interacts with these other factors. We know something about cigarette smoke, about tobacco smoke and radiation, but for most of the other important factors that generate the background risk that there is in general populations, we don't really know very much. Breast cancer, female breast cancer, is one of the exceptions in ICRP, and that is just the absolute risk that is moved across from the Japanese population to all these other populations, no matter what the background risk of breast cancer might be, which is very interesting because it says that the assumption is that breast cancer does not interact with other factors, even though breast cancer varies quite a bit, around the world. And it was low in the mid-20th century Japanese population. It was high in the Western populations. But apparently that doesn't matter. So, which is interesting in itself. Thyroid, for example, is exactly the other way around. It's 100% relative risk transfer between populations. So all that was really just to say interaction is important. We currently assume an interaction for most cancers of some sort or another. So, knowing more about that is going to be very important indeed in the way that we develop, radiological protection. Anyway, that was just to sort of open up the discussion generally. And if any issues that have been raised this afternoon or related issues, please contribute now and say, have your say. Anyone? Come on, Dominique. I know you. Right.
I think in the morning there were. Sorry. In the morning there were a few questions by Professor Nakamura, and also Andre asked about strain differences in animals, and then what is its relevance to humans. And I was thinking that the genetic makeup itself may be different, because we know that DNA repair deficiency makes the radiation effects more stronger, or DNA repair deficiency. Deficient cells are highly sensitive to ionizing radiation, for example. So that way, maybe we can compare strain difference, but you don't have strains in humans, for example. But genetic makeup may be one of the contributing factors in that. Probably. When we talk about breast cancer, for example, undergoing therapy, 5% of breast cancer is hereditary in nature, right? So whether the fetus is BRCA1 mutant, if that is the situation, then the cells from this embryo will be sensitive to radiation than the other, normal embryos, for example. So that's one of the other factors to be considered as well. I guess that's debatable, but still I think it's relevant to put it in genetic makeup or DNA repair proficiency and deficiency, for example. I didn't put up genetics as one of the factors in other factors in my presentation, because that's probably is one which we need to consider as well. I think there is another task group looking at radio sensitivity. Yes, 111. Yeah. So, which is relevant for this. Yeah, exactly.
I just wanted to follow up on some of the things that Prakash, you mentioned, which was ultrasound. You didn't say anything about MRI. And I worked a lot on looking at safety. Well, it's important, though, because a lot of women now in developed nations get, it's ubiquitous. Everyone gets an ultrasound before their baby is born, because they get fetal surveys. But they also get MR when there's a question about a congenital malformation. And it's akin to a genetic marker. If you're really good at it, you can detect many genetic anomalies, particularly in the CNS. And so, I was part of looking at certain centers, have centers of excellence, and they look for genetic anomalies and try to help the family make decisions about abortion or not at before 20 weeks. And so this question about MR safety, about heating, so it's heating and acoustic noise it has been important. And there was an article in 2016, JAMA, I think it was JAMA, of tens of thousands of pregnant women and their outcomes with MRI to look at concerns. It was epidemiology, and it was showing that there was no increased evidence of poor fetal outcomes unless they had gadolinium, the contrast agent. If they had gadolinium, there were associations with autoimmune disorders, so rheumatic diseases, which was interesting, because there's been some reports about adults who have gadolinium with their MR and those disorders. So that's just something to keep in mind, that nothing is without a cost. You may avoid the ionizing radiation, but you have other issues. Yeah. And then the other comment I was going to make is about the publication 90, where it lists the cancer predisposition syndromes. And I think you mentioned, Prakash, that there's just a growing list of these syndromes that we can identify. And it's important that, at least in the pediatric community, imaging community, we recommend that if we identify these people, these children, we recommend that they not get ionizing radiation imaging, if possible. The problem is that most of the community of radiologists in the world don't know this, or the children may not be identified as having the syndrome. But once they do, either the children or the adults, when they get diagnosed with Li-Fraumeni or whatever syndrome, then they get a workup and their family gets a workup. Thanks.
Thanks, Kimberly. Anyone else want to? I was interested in ultrasound, because the Oxford survey of childhood cancers looked at ultrasound and didn't find anything. I mean, these was of course in the days when it was starting to be introduced. I mean, the Oxford survey started in the early 1950s and went on into the 1980s. So I can't remember the exact publication where that was in, but they did start looking at it, and unlike for ionizing radiation received in utero, and of course the Oxford survey was the big study. What?
Tell them that the fetal brain should not get high.
Yeah, I can't hear.
Dwell time. There's a dwell time effect.
I can't hear.
Yeah.
Well, there is a dwell time effect of power Doppler on fetal brain. So we have guidelines on ultrasound of the fetus and the brain, and not using color Doppler or duplex on the brain. So there are limits of what we are allowed to do, and that's still true today, even with better machines. But the better machines make you want to spend more time investigating the vasculature in the fetal brain.
Right, and it is surprising how issues arise that weren't anticipated. I always think of birth weight and the influence of birth weight on childhood cancer, childhood leukemia, childhood cancer, which sort of came in the past couple of decades, maybe. The heavy babies are more susceptible to childhood cancer. And in the Oxford survey of childhood cancers, which Alice Stewart kicked off in the 1950s, they looked at all sorts of things, maternal age, birth order, and all the rest, but they didn't collect birth weight, strangely enough. and I remember John Bithell who was one of Alice Stewart's collaborators, who died in 2020, was very concerned that this was a confounder for the antenatal X-ray association that was found by the Oxford survey. And you can imagine that a heavy fetus, a big fetus, is more likely to be X-rayed than the smaller fetus. So it's quite it turns out from Brian McMahon's study in the US, in the Northeast US, and they did have birth weight data, that it doesn't look like that it's a major confounder. But it just goes to show how these things can creep in at a later date when they weren't suspected, early on. And birth weight, I always think, well, gosh, birth weight, who'd have thought birth weight? And there it is. And a potential confounder, which doesn't look like it is, but there we go. Anyone else wish to make any points on this on these visually? What? Yep, sure. Of course.
Comment to the previous comment about this imaging, because when you are doing it for purpose, it's one thing, but there are many parents who are doing just for making pictures, 3D picture, Oh, yeah. So it's another way, to see. So for recommendations, no?
Oh, right. Okay.
Actually here, okay, I understand. I have a couple points to stimulate the discussion. One is short and simple. On the definition of transgenerational effects, early in the morning, we discussed what is transgenerational, what is intergenerational. We haven't discussed what is multi-generational. So apparently in the animal experimental design, you need to go up from F3 to call it transgenerational, because the germ cells of the fetus is exposed. Now, in human situation, in real situation, there could be scenarios, I think briefly mentioned by Kimberly, when a pregnant woman can be exposed, or parts of her body can be exposed without actual exposure of the fetus. So if the fetus doesn't get a radiation dose, but F0, a woman gets exposed, and then we observe effects in F1. Is it a transgenerational effect? Can we call it transgenerational? Or we can still not call it transgenerational effect. So this is a question for discussion. And a second point, quite different. It relates to two previous presentations earlier today. One is on the review of the human studies by genetic effects in human populations by Evgenia, and one of the a second talk on the FOCS cohort from Japan. So earlier genetic studies on human populations, most of them were done by Yuri Dubrova using the mini-satellite mutation frequencies in mini-satellite regions or tandem repeat regions, which occupy a significant portion of human genome, I think up to 15%. Compare this to 3% of actually gene encoding region, and finding effects, finding mutation rates increased. And then the last year Chernobyl study using full genome sequencing, where no genetic additional mutational burden was found. So I think this is inconsistency which should be addressed. And related to this, there's a question, maybe some people know from the audience today, in the Chernobyl population, when they performed whole genome sequencing, did they actually do long repeat sequencing and capture these tandem repeats, or they did not? Because if they did not, maybe those two results are not inconsistent, in fact. Or if they did, then there's inconsistency that should be addressed. So if anybody knows, I don't know, it's open to discussion. And I just agree with the previous speaker that long repeat sequencing is a key, because not only capturing structural changes, but also mutation, single nucleotide mutations in those tandem repeat and retrotransposon regions is extremely important. So those are two different.
Yeah, many thanks. Thank you. We have one up there, but it seems to have gone.
Yeah, I can ask now if that's okay.
Yes, please, go ahead. Yeah.
So this is to Dr. Grant, but just open for discussion. I think one of the complications studying the atomic bomb is that they weren't exposed to radiation in isolation, as we know. One thing that Prakash mentioned that I'm curious about, has anyone actually quantified the thermal impact of the bomb? Because obviously the closer you are to the hypocenter, I imagine they may have been exposed to increased temperature, albeit very short time frame. But I'm just curious, has anyone considered the thermal aspect of the bomb when looking at results?
Well, Eric is coming forward. Shaking his head.
The only thing that we have that might be helpful would be flash burns. We do have data on flash burns, and whether or not we'd find something there, I don't know what to say. But there are some data on flash burns. So whether or not that will be helpful, I don't know.
Yeah, thanks, Eric. That's that's interesting. I'd forgotten that. All right. Yeah.
No, it's just something that came to my mind. I was watching my boss presentation, Augusto. And also Evgenia earlier in the morning. So we have some cohorts, and then we can study the dosimetry, like the external dosimetry, internal dosimetry in workers or people exposed to the nuclear bombs or great accidents. But what about the hot topic today, that is radium and norm? So I have not run any searches on that. So this is just for discussion if anybody knows about it. But now we have strict regulations on radium because of the lung cancer and so on. What about the exposure of the women? Because it's not the same as comparing a woman in daily basis with a woman in the nuclear bomb. It's different environments, different kinds of exposures, inhalation or ingestion or external exposure. So, something just came to my mind.
No, it's not a reply, but I'm continuing on your. Well, actually, I had separately from you thinking about it, because it's actually the difference between animal studies. It's also that when we are doing animal studies, all animals are in the same place, no? But humans are moving, and actually we are doing evacuation. And this topic I think I raised before in other presentations. So when we are evacuating people, like in Belarus, for example, from south of Belarus after the Chernobyl, they were evacuating on the north, where we had high levels of radon. Can you imagine? They received there, and then they moved after, and they received even more. So we had more incidents. Of course, even if people are part of stress, psychological stress, that people, when they shift from one area to another, the same thing I think in Japan, in the south, they have also more radon. So we should take into account maybe in recommendations also when we are suggesting some kind of evacuation or moving people are part of possible, these effects can be even worse, because we are doing, these other factors. So this movement from psychological point of view and of other environmental factors that can be doubled, maybe, or I don't know, effects. Actually, in that time, I don't know, Evgeny, if you remember, maybe no. We had like kind of rumor, because it was like suggested that people who are in the contaminated zone just don't move; they are adapted to radiation. So it's better not move, because when they move, they feel worse. But I think it was more related to this such other laws, but not like this. But we should take into account this, maybe. Thank you.
Okay, thanks. Yeah, but I have one more, because the reason I say that is I know all these partitions are going to be coming across for the next. So,
okay, yeah, thank you. Yeah, just again for the discussion, I will maybe tell you more about biological effects later on this afternoon. But my question, let's say, how biological studies can better contribute to risk estimate. This is a very, I think, crucial question. So for people doing biological effects, so when we see, let's say, the studies are not much taken into account in risk estimates.
Yeah, well, that's a very profound profound issue to finish on. But so I mean, bear that in mind, because we're now. It's gone. But we're now going to have a coffee break, and then we're going to break up into the four separate groups. These partitions will come across. So this is going to be A. This is going to be B. This is going to be C, and then D is in the next one, right? Right. Yeah, in the next one. So it's all going to change. So you better take your bags and things out.